Your smartphone would weigh 2 pounds and be an inch thick. A can of Coca-Cola would cost $5. A Boeing 747 couldn't fly across the Atlantic. It would run out of fuel halfway there, all because of one metal humans didn't discover until 1828 and couldn't mass produce until 1886. Before that, the world ran on iron, steel, copper, and bronze. Metals too heavy, too expensive, or too weak for modern life. Today, we're going inside the factory in New York where this metal gets made, and I'll show you what properties are created at each step and what would happen if we had to use something else instead. The Alcoa aluminum plant in Massena, New York, sits on the St. Lawrence River 80 miles north of Syracuse. It's been producing aluminum continuously since 1902, and this location works because it has direct access to massive hydroelectric power from the river, which is critical because making aluminum requires more electricity than almost any other industrial process on Earth. The raw material is bauxite ore, arriving by ship from Jamaica and Australia as reddish-brown powder. If aluminum had never been discovered, we'd still be mining iron ore for everything. Steel production requires coal and produces massive carbon emissions, while aluminum runs on clean hydroelectric power. Without aluminum, global carbon emissions would be roughly 15% higher just from metal production alone. The first stage processes bauxite in the Bayer process. The ore gets mixed with caustic soda and heated to 350 degrees Fahrenheit under pressure, dissolving aluminum oxide while leaving iron and silicon as red mud waste. What emerges is pure white aluminum oxide powder called alumina. This creates aluminum's first critical property, incredible corrosion resistance. If we used steel instead, every outdoor structure would need constant repainting. The Statue of Liberty's copper skin turned green from oxidation, but aluminum would still look silver white today. Steel ships need dry docking and repainting every few years. Aluminum boats last decades with zero maintenance. Without this, coastal cities would spend billions more on infrastructure upkeep. The alumina moves to the electrolysis hall, containing rows of reduction cells, glowing rectangular pools 15 feet long, filled with molten cryolite at 1,750 degrees Fahrenheit. Alumina dissolves into this bath. Then, 150,000 amps of current passes through each cell. Enough electricity to power 15,000 homes. Pure molten aluminum sinks to the bottom, while oxygen bubbles up. This is the Hall-Héroult process from 1886, still the only economically viable way to produce aluminum. Before this process, aluminum cost more than gold. Napoleon III used aluminum dinner plates for important guests, while others ate off gold. Without Hall-Héroult, aluminum would cost $300 per pound today, making a soda can worth $250. After 24 hours, molten aluminum gets siphoned off and poured into crucibles holding 10 tons each. This glowing metal demonstrates aluminum's most important property, strength to weight ratio. Aluminum is 3 times lighter than steel, but when properly alloyed, nearly as strong. A Boeing 747 made from steel would weigh 1,200 tons instead of 400. You'd need engines 3 times more powerful, burning 3 times more fuel. But carrying that extra fuel adds more weight, requiring even more fuel. The tyranny of the rocket equation makes long-distance flight impossible. Without aluminum, commercial aviation doesn't exist. You might have short flights on steel aircraft, but New York to London would require 2 refueling stops, turning 8 hours into 20 hours and costing $5,000 per ticket. Molten aluminum pours into molds creating ingots. Then these get reheated to 800 degrees and passed through massive rollers creating sheets from 0.0002, 5 inches thick to several inches thick. This rolling aligns the grain structure for specific properties. Aluminum's electrical conductivity becomes critical here. It conducts 60% as well as copper, but weighs only 30% as much. Every high-voltage power line uses aluminum wrapped around steel. If we used copper instead, transmission lines would be 3 times heavier, needing support towers 3 times stronger and spaced closer together. Building a power grid would cost 4 times more. Rural electrification wouldn't have happened. Your monthly electric bill would triple. Every sheet goes through rigorous quality control, and there's a specific reason aluminum inspection is so strict. On April 28, 1988, Aloha Airlines Flight 243 was cruising at 24,000 feet over Hawaii when passengers heard an explosive decompression. The entire top section of forward fuselage had ripped off, tearing away 18 feet of aircraft skin and exposing the cabin to open sky. One flight attendant was swept out and killed. 65 passengers were injured. The investigation revealed the aluminum fuselage had developed microscopic cracks from metal fatigue after years of pressurization cycles. These tiny cracks had grown and joined until the structure failed catastrophically. The aircraft had made 89,000 flight cycles, and inspection techniques couldn't detect cracks that small. That tragedy transformed aluminum inspection in aerospace. Today, every sheet goes through eddy current testing, detecting surface cracks as small as 0.005 inches deep, ultrasonic testing finding internal defects, and X-ray inspection for critical parts. They also do fatigue testing, bending samples millions of times to verify the alloy can handle stress cycles. The rejection rate for aerospace-grade aluminum is 12%. 1 out of every 8 sheets gets melted and reprocessed. The aluminum that passes inspection ships to manufacturers, making everything from aircraft to beverage cans. The Massena plant produces 270,000 tons per year. Without aluminum, beverage cans would be tin-plated steel weighing 3 times as much. A 12-pack of Coca-Cola weighs 24 pounds instead of 8. Shipping costs triple, prices double. You're paying $5 for a single can. Building construction would be completely different. Modern curtain wall facades use aluminum frames, strong enough for glass, but light enough that buildings don't need massive reinforcement. Without aluminum, you're back to small windows in thick walls, or steel frames so heavy that buildings over 50 stories become impractical. The modern glass skyline doesn't exist. Computers and smartphones would be radically different. The aluminum unibody making a MacBook possible would have to be plastic or magnesium. Plastic isn't stiff enough and cracks. Magnesium is light, but catches fire during machining. Your laptop weighs 5 pounds instead of 2.5, is twice as thick, costs more. Your smartphone has a plastic body that cracks when dropped, weighs 10 ounces instead of 6, is an inch thick because you need extra structural support. The Alcoa plant has run for over 120 years, producing roughly 20 million tons of aluminum turned into aircraft, cars, buildings, power lines, packaging, and electronics. Without the Hall-Héroult electrolysis process running in those reduction cells, none of this exists. We're stuck in a world that's heavier, more expensive, more polluting, and more limited. You've seen how bauxite transforms at 350 degrees into alumina, how 150,000 amps separate aluminum from oxygen in molten cryolite, how rolling creates sheets with properties no other common metal can match, and why 12% of aerospace aluminum gets rejected, because lessons from Aloha Airlines are built into every inspection. If this alternate history interested you, subscribe for more deep dives into materials making modern life possible. Thanks for watching. In every second of our lives, there are metals we don't even suspect. Without them, there would be no smartphones, electric cars, or even jet aircraft. And now imagine a place where, in the middle of the desert, under the scorching California sun, the United States creates a strategic resource of the future, without a single pound of Chinese raw materials. Here, at Mountain Pass, they mine 43,000 tons of rare earth metals annually. Rocks that look ordinary are transformed into materials for lasers, engines, and defense systems. But there's something almost no one knows about. And if you watch till the end, you'll understand why this dust from the desert can change the world. Today here, in the dust and heat, MP Materials Company mines 43,000 tons of rare earth concentrate per year, all without a single pound of Chinese raw materials. For a country that for decades depended on imports from China, this is a strategic breakthrough. The main star of this place is Bauxite, a mineral that looks like an ordinary stone but contains treasures inside: lanthanum, cerium, neodymium, and praseodymium. These very elements give life to modern magnets, lasers, electric cars, and jet aircraft. Everything begins in the depths of the quarry. Huge excavators and 300-ton trucks carry rock to the crusher. Next comes the flotation process, similar to a magic sieve. Crushed ore is mixed with water and special reagents. All this turns into foam, and Bauxite particles float to the surface, while waste settles to the bottom. After flotation, Bauxite goes for chemical expertise. In MP Materials laboratories, it's transformed into concentrate, and then into individual elements. This is a complex sequence of extractions and washes, where each metal chooses its own path. Once, this stage was performed in China. Now the United States is gradually building a full production cycle, from ore to finished magnets. Thanks to this, the country has already replaced 80% of its former imports from Asia, and this is just the beginning. It sounds like science fiction, but it's a fact. 2 pounds of cerium can become material for optical lenses of laser systems in military equipment. Other elements, like neodymium, are used in powerful magnets of jet engines and in missile guidance systems. All this means that every ton of ore from Mountain Pass isn't just raw material. It's a piece of American defense independence. The California desert isn't just scorched by the sun. It's politically charged. Mountain Pass is a symbol of a new era where technology and geopolitics merge. Today, American engineers, in hard hats and safety glasses, are literally building their own supply chain of the future, step by step displacing the Chinese monopoly. Just as in the 60s, when the United States first launched a satellite, now they're trying to be first to build an independent rare earth elements industry. And it all starts right here, among the sands, where it was once quiet, but now machines rumble, and the fire of smelting furnaces glows. If you gather all the rare earth elements mined here per year, it's 43,000 tons of concentrate. Outwardly ordinary dust, but actually strategic raw material, more valuable than gold. And if this dust were transformed into finished products, it would power more than 100,000 electric vehicles. Those that race without a drop of gasoline, thanks to neodymium magnets in motors. The same metals would ensure the operation of hundreds of guidance systems for F-35 fighters, where precision depends on microscopic lasers and sensors. And also, tens of thousands of medical lasers used for eye surgeries or to stop bleeding in military hospitals. The irony is that Mountain Pass isn't a megapolis or a Silicon Valley laboratory, but a patch of land in the middle of the desert. But it's precisely this place that's becoming a PowerPoint again. Every kilogram of cerium mined here is a potential lens for lasers in defense systems. Every gram of neodymium is a piece of an engine for an electric car or satellite. It's worth talking separately about cerium. Cerium isn't just another metal on the list of rare earth elements. It's one of those that sits quietly beneath the surface of technologies, but without it, the modern world would look completely different. Imagine a desert quarry, drilling rigs, machine cries, and dust, and among all this, under sand and stone, hides a complex chemical actor that transforms from an ordinary mineral into a material that affects aircraft, phones, and even medicine. In appearance, an ordinary grayish powder, nothing special. But this is a true alchemist among metals. Without it, there would be no clean glass in telescopes, no shine in smartphones, no precision of lasers, and no cleaner air from automobile exhausts. 1 gram of cerium can do what other materials can't even in hundreds of times larger quantities. Cerium is a true master of transformations. In catalysts, it behaves like a chemical chameleon. It intercepts and releases oxygen, converting harmful gases into harmless ones. In glass, it extinguishes ultraviolet light, makes lenses transparent as crystal. Its oxide polishes phone screens, cameras, optical devices, literally erasing microscopic scratches from surfaces to perfect smoothness. Among workers at the plant, there's a joke. Without cerium, the world wouldn't shine. And there's truth in this. Because when it gets into engineers' hands, everything around starts to shine. Literally. It helps see farther, move faster, burn cleaner, heal more precisely. All this, from desert dust, from a place where heat reaches 110 degrees Fahrenheit, and wind sweeps away traces in a few minutes, as a symbol that even in the driest desert, the future can be born. Mountain Pass was once just a point on the map, the only mine of this type in all of North America. But now it's surrounded by an entire network of structures that transform crude ore into pure elements, ready for the most complex technologies, from electric motors to jet guidance systems. MP Materials Company has built here not just a mine, but a closed-cycle production, something America lost back in the 1990s when all supplies depended on China. After many years of research and investments in hundreds of millions of dollars, new lines operate almost without human participation. All processes are controlled by computers. Sensors measure compound purity, robotic cranes move containers, and special cameras capture every dust particle. Air in laboratories is so sterile that it feels like it's not a desert, but a space station. Everything that comes out of these shops is sent to other factories, which are also being built inside the country. In Texas and Ohio, they're building factories that will manufacture permanent magnets, precisely those that ensure the operation of Tesla electric motors, wind turbines, or fighter guidance systems. Once these magnets were supplied from China almost 100%, but now America plans to completely switch to its own materials by 2030. People who work here say they feel part of something bigger than just production. When they watch as a substance comes out of desert soil that will later turn into part of a satellite or a high-precision laser, it resembles a true miracle. Next to the quarry grow warehouses, laboratories, transport hubs, and on the horizon, also solar panels that power this giant. After the mine closed in 2002, when Chinese companies effectively monopolized the rare earth elements market, only a few dozen workers remained in the Mountain Pass area, maintaining security and basic infrastructure. The nearby settlement declined. Stores closed, roads overgrew with weeds, and local families moved out to look for work. When in 2017, MP Materials Company bought out the assets and launched a modernization program, the situation began to change literally from scratch. Over several years, more than 800 jobs were created at the enterprise itself, not counting hundreds of related ones, in transport, chemical supply, technical service, energy, and even local services. In neighboring towns, cafes reopened, schools received funding, and roads, repairs. Besides direct vacancies, MP Materials launched a professional training program, cooperating with local colleges. Graduates of technical specialties can now do internships right at the modern processing plant, where they learn to work with automated lines, flotators, hydrocyclones, and chemical separation systems. Interestingly, jobs here are very diverse, from geologists, chemical engineers, process operators, to programmers and data analysts who control plant operations through digital panels. Each shift means tens of thousands of parameters read by sensors in real time. In a broader sense, the revival of Mountain Pass has become a symbol of the return of American manufacturing, which for decades was exported abroad. Against the background of political statements about reshoring and strengthening the internal supply chain, this project is often cited as proof that even in the desert, you can create a modern, profitable, and stable industry. This single tank holds an entire Olympic pool's worth of fuel. Hard to believe. Look at this, 10,000 gallons in each one of these tankers. I'm standing here in a massive, towering factory right in the heart of America, where these steel giants are born from scratch. This isn't just a workshop, it's a true industrial cathedral, where instead of organ music, you hear the roar of metal, And instead of incense, you smell ozone and white-hot steel. Today, we're diving into the process of building a fuel tanker. Those same shiny cigar-shaped missiles that race down highways, loaded with gasoline or diesel. I've already walked these floors, talked to workers whose faces are hardened by heat and labor, and now I'm going to tell you everything. To do that, you need to follow me. Don't fall behind. Ready? Then let's roll. This is going to be incredibly fascinating. First comes the raw material, the lifeblood of a future giant. It all starts not with ore, but with perfectly flat, thick steel sheets arriving on railroad platforms. Picture a sheet of metal 25 feet long and 10 feet wide. It's like a small billboard, only made of steel. And this steel isn't ordinary. It's a special alloyed blend containing chromium for rust resistance and molybdenum for incredible strength. It's engineered to withstand insane pressure, impacts, and constant corrosive attack from fuel. Each of these sheets weighs 3 tons. Workers in bright hard hats, like ants around a giant treasure, use overhead cranes gliding smoothly beneath the ceiling to lift these sheets and carefully stack them. Everything's computer controlled, with laser scanners checking every millimeter of surface for detected defects, microcracks, or irregularities. Only perfect raw material gets the green light to move forward. Now it's time to cut the metal. Sheets roll from the warehouse onto the cutting table. A portal looms over the sheet, and a cutting head hisses along its track. This is a giant plasma cutter. From the nozzle, under massive pressure, erupts a jet of gas heated to tens of thousands of degrees Fahrenheit. It's like a tamed lightning bolt. That jet slices into the metal like butter. Sparks fly in every direction. Like fireworks, the air hums with power, and the smell of ozone fills the shop. A computer program guides the cutter along a perfectly calculated path, carving 2 or 3 panels for the future tank from a single sheet with accuracy down to a 1/4 inch. Each panel has all the necessary openings for future valves and hatches. After cutting, the panels are still hot and a bit rough around the edges. Next up, bending the panels, giving them shape. That's where the real heavyweights come in. 200-ton hydraulic presses. Picture a giant machine that slowly, but with unstoppable force, bends thick steel plate like it's a sheet of paper. A crane feeds in a flat panel, and the machine, pressing it against a massive curved die, transforms it into a perfect arc. That's how the cylindrical sections of the tank and the rounded ends are born. The cylindrical body gets assembled from several of these sections and ends up 50 feet long and 10 feet in diameter. After each bend, workers check angles and radii using special templates and tape measures. Everything has to be perfectly round. Why? Because in a circular vessel, pressure distributes evenly. Any warping, any flat spot, that's a stress point where, under fuel pressure, the tank could rupture. Fuel doesn't tolerate compromises. Welding. That's where the heart of the process is, where separate pieces become one whole. This is where real craftsmanship lives. Welders in masks with automatic ultraviolet filters aren't just handling simple equipment, they're operating automated submerged arc welding systems. That means the welding robot runs along the entire seam, and the arc itself burns not in open air, but beneath a thick layer of special flux powder. This creates a perfectly clean, deep weld, 1/2 inch thick, that's actually stronger than the metal itself. After welding, our tank is one piece, but it's stressed out. Welding creates internal tensions in the metal that need to be relieved, so it's heading for heat treatment. A giant crane carefully lowers the entire 50-foot tank into a massive furnace. The doors close, and the temperature inside slowly climbs to 1,600 degrees Fahrenheit. It rests in that oven for about an hour. This process makes the metal more elastic and releases all the stress. Then the doors open, and out comes a red-hot monster, steam pouring off it. Workers in silver suits start hosing it down with water for controlled cooling. The air fills with a loud hiss, like 1,000 kebabs hitting the grill at once. I laughed and told the guys, "This is your sauna." Now for painting and coating. The cooled tank gets sent to a paint facility. This thing's the size of an aircraft hangar. Then comes the first layer, an epoxy primer that protects against rust. After that, 2 coats of top coat, white for better visibility on the road, and silver with added aluminum powder to reflect sunlight so the contents inside don't heat up. But what's on the inside? That gets special protective coatings. A thin but incredibly tough layer of polyurethane, just 10 millimeters thick. It's completely inert, doesn't react with fuel, and won't crack from vibrations. Workers use laser thickness gauges to check every square inch. No gaps allowed. Installing the fittings is the final touch that transforms the barrel into a high-tech tool. They mount the valves, fill valve on top, drain valve on the bottom, plus an emergency valve to release excess pressure. Each valve is a work of art made from stainless steel, rated for 200 pounds per square inch. They install electronic sensors for fuel level, temperature, and pressure. All the data feeds to a computer in the driver's cab. They mount an inspection hatch, 2 feet in diameter, with hermetic seals. I climbed inside an empty tanker myself, space like a space capsule, and absolute silence, because the 1/4-inch thick walls perfectly dampen sound. Testing, the most exciting and critical stage. First up, hydraulics. They fill the tank completely with water and pressurize it to 250 pounds per square inch. Inspectors with flashlights walk around it for 2 hours, hunting for even a single drop. If there's nothing, the tank is sealed tight. Next, the vacuum test. They pump out the air and check if the pressure drops. And the final, most precise test, pneumatics with helium. They fill the tank with pressurized helium, and special sniffer sensors check for the tiniest leaks. If not even a microscopic helium atom seeps through, the tank is ready for fuel. I watched them fill one test tank with 10,000 gallons of gasoline. Not a whiff of smell outside. The final stage, inspection and marking. A special plate gets stamped with a serial number, manufacturing date, and the empty tank's weight, 20,000 pounds. They slap on Department of Transportation certificates with all the safety specs. And then, a giant crane carefully lifts the finished gleaming tank and mounts it onto the truck chassis. Now it's ready to roll down the highway. Guys, this factory only produces 2 of these tanks per month. Each one's like a little mobile fuel fortress, incredibly safe and reliable. I'm absolutely blown away. From a simple steel sheet to a finished tank, every single detail is thought through. If you see these tankers on the road, know there's incredible work behind them. Thanks for watching. Hit that like button, subscribe, and I'll see you on the next factory tour.
This is the biggest warship the world has ever scrapped. 1,100 feet of steel, 90,000 tons. And buried deep inside the hull, where no torch can just cut its way in, sit 8 nuclear reactors. Not 2, 8. This was the first nuclear aircraft carrier ever built, and taking it apart is turning out to be harder than building it. The Navy now says the job will swallow more than $1 billion and stretch past 15 years. 15 years to take one ship apart. Here's the thing nobody tells you. Before a single saw touches that hull, the most dangerous part has to come out first. And it has to come out in one piece. Watch to the end, because the way they handle those reactors is the part the press releases skip right over. Let's back up and look at what they're actually dealing with. The USS Enterprise. The crew called her the Big E. She slid into the water back in 1961, the first carrier on Earth to run on atoms instead of oil. And for over 50 years, she sailed every ocean we've got. Then, in 2012, the Navy pulled her out of service for good. And that's where the real problem started. Because you don't park a nuclear ship in a field and walk away. Every system on board has to be drained, stripped, and made safe. First come the weapons and the classified gear. ripped out and hauled off under guard. Then the fuel oil, the hydraulic fluid, the lubricants, thousands of tons of liquid that can't just be dumped. Asbestos gets pulled from the walls, PCBs, lead, every toxic thing built into a Cold War warship. All of it tagged and bagged. And only after the ship is gutted and clean can anyone start thinking about the reactors. That alone takes years before the hard part even begins. Think about the scale of it for a second. This ship was a floating city. She had her own power plant, her own hospital, her own water-making machines, miles of cable running through her like veins. 4.5 acres of flight deck up top, 2,000 compartments below. Stripping a building that size would be a job on its own, and this building floats, and parts of it are radioactive, and every bolt of it was designed by the military to survive a torpedo. Nothing about pulling her apart is easy. Nothing about her was meant to come apart at all. So why is this one ship such a nightmare? 2 words: 8 reactors. A modern Nimitz-class carrier runs on 2. The Enterprise was the prototype, the first of her kind, and the engineers of the late 50s weren't sure 2 would be enough to push a ship this size. So they packed in 8 smaller reactors instead, each one feeding the turbines, all of them crammed into the belly of the hull. That made her fast, and it made her legendary. It also made her a problem nobody had ever faced, because now every one of those 8 has to be defueled, shut down cold, and dismantled. The good news, and it's real, is that the defueling is already done. The actual nuclear fuel, the spent uranium that powered her for decades, has been removed and shipped off to secure storage. But the reactors themselves, the steel vessels and the piping around them, those are still radioactive. And that is the wall every plan runs into. You can't just send a torch in there. Metal that's been sitting next to a reactor core for 50 years soaks up radiation. The steel itself becomes hot, not warm to the touch, but hot in the way a Geiger counter screams. Cut into it blind, and you spread that contamination into the air, into the water, onto the men doing the cutting. So before anyone goes near it, engineers map every inch of that compartment, measure the radiation point by point, and figure out exactly where the clean steel ends and the dangerous steel begins. It's slow, careful, expensive work, and there's no shortcut around it. Here's where it gets strange, and here's the part the headlines breeze past. The reactors don't get cut up on site like the rest of the ship. They get removed whole. Each reactor compartment, a massive sealed chunk of the hull, the steel vessel and all its contaminated plumbing, gets cut out as one giant block, capped, sealed shut, and lifted out in a single piece. We're talking pieces that weigh hundreds of tons each, hoisted by some of the largest cranes on the planet. They go on a barge. For the Navy's submarines, those reactor compartments travel by water all the way to a desert site in Washington state, a guarded trench called Trench 94, where they're buried in the ground to sit for thousands of years. The Enterprise is bigger, more complex, and the Navy is still deciding whether to send her to a government yard or hand her to a commercial shipyard. But the principle is the same. The hot part comes out first, sealed, and goes somewhere it can be watched for a very, very long time. Only then does the real scrapping begin. Now the ship is finally just a ship. A hollow shell of steel, no fuel, no reactors, no poison left inside. And this is where it turns into the biggest recycling job you'll ever see. They float her into a dry dock, pump the water out, and the carrier sits there, exposed, keel to flight deck, like a beached whale made of metal. Then the torches come out. Workers in cutting gear swarm the hull, slicing it apart section by section, plate by plate, the way you'd take apart an engine, but on a scale that's hard to even picture. The flight deck comes off, the hangar bays come down, the island, that tower where the captain stood, gets carved away. Every piece gets sorted, and the numbers are staggering. A carrier this size holds somewhere between 60 and 90,000 tons of steel and metal, and almost all of it can be recycled. That steel goes back to the mills, gets melted down, and comes out again as rebar, as beams, as the bones of new buildings and new cars. A warship that once carried 5,000 sailors ends its life as the frame of a parking garage you'll drive through without ever knowing. And it isn't just steel. There's copper in the wiring, thousands of tons of it, worth a fortune on its own. There's bronze, aluminum, brass fittings, and deep in her belly, 4 bronze propellers, each one the size of a house, each one worth millions just in raw metal. By the time they're finished, almost nothing is left to throw away. A ship that cost billions to build gets weighed, sorted, and sold off by the ton. And here's the math that should stop you cold. A brand new carrier today, a Ford class, costs around $13 billion to build. $13 billion. To take an older one apart safely costs over $1 billion more and eats 15 years. So every nuclear carrier represents a bill at both ends. One to build her, another huge one just to make her disappear. That's the hidden price of a nuclear navy that almost nobody talks about. The Big E was the first to face it, the prototype for a problem the whole fleet will inherit, because every Nimitz built after her is going to need this exact same treatment, one by one, for decades to come. So the next time you see a carrier on the news, remember, that ship has 2 lifetimes. The one where she rules the ocean, and the long, quiet, expensive one where the world has to figure out how to take her back apart without poisoning anything. And if you want to see how the most dangerous machines we've ever built get torn down and turned back into raw metal, you're in the right place. The next one is already in the dry dock.
What if the most dangerous part of a suspension bridge isn't what you see? Because inside those main cables, which look like solid metal, there's a hidden structure made of tens of thousands of wires, each one vulnerable to destruction, even from a single drop of salty fog. So why doesn't a bridge weighing thousands of tons collapse every single day? And what happens if moisture gets inside the cable where nobody can spot it? Stick around until the end. You'll discover a secret even bridge engineers don't talk about. The classic example, the Golden Gate in San Francisco. It's got 2 main cables slung over the towers and anchored into massive concrete blocks in the rock. Each cable's diameter? About 37 inches. We're not talking rope here. This is basically a steel column so thick you'd need 2 or 3 people linking arms just to wrap around it. Inside? 27,572 individual wires, compressed into a perfectly round bundle. Unwind all those wires and lay them end to end, you'd get roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. The weight of just one cable? Close to 24,500 tons. That's comparable to a small cruise ship or a few hundred fully loaded semis. Why use so many individual wires instead of one giant solid rod? Here's the thing. Steel works great in tension, but it doesn't handle defects well, especially in large cross-sections. When an element consists of thousands of independent wires, each one can play a little, taking on a bigger share of the load here, a smaller one there. If for some reason a single wire corrodes or weakens, its share in the overall strength is minimal, and you won't even notice it in how the entire cable behaves. Plus, it's way easier to create a flexible shape from tens of thousands of thin elements. The cable can smoothly wrap around the towers, forming a huge parabola over the span, whereas a rod of that diameter simply won't bend without plastic deformation. The process of creating main suspension cables is also nothing like how regular steel cables are made at the factory. Nobody sends a finished cable to a construction site that's 3 feet thick and thousands of feet long. That kind of monster would be impossible to deliver or hoist into position. So the main cables of suspension bridges are spun on site. It starts with installing temporary pilot cables between the towers. A traveling carriage runs along them, shuttling back and forth across the entire span. A reel of steel wire is mounted on the carriage. Each trip of the carriage pulls another wire between the shores. One end of the wire is anchored on one side. The carriage holds the reel across the span. The wire is secured on the other shore, and the excess is cut off. Then the next wire, and this happens tens of thousands of times. To keep this insane marathon from turning into chaos, the wires are organized into so-called strands, or sub-cables. For example, several hundred parallel wires are bundled together into one strand of a specific diameter. First, all the wires get pulled tight with a bit of slack. Then, special jacks even out the tension, so each individual wire carries roughly the same load. Next, the bundle gets clamped with rings, or special clamps to keep it from splaying apart. Once you've got enough of these bundles, they're brought together and clamped again into one massive structural cylinder. A spiral wrapping of thin round wire goes on top to hold the shape, plus a protective layer of paint or other anti-corrosion coating. At this stage, the cable can already hold an incredible amount of force. Picture this. Hanging from it is a bridge span, a steel truss or box girder that supports the roadway. This span transfers its load through suspender cables onto the main cables. Every vehicle crossing the bridge adds several tons to the system, sometimes dozens if we're talking about a semi or a convoy of trucks. Wind pushes against the structure's lateral surface with forces that can reach thousands of kilonewtons during a storm. Ultimately, the main cables feel all of this, stretching literally a few inches along their entire length while staying within elastic deformation limits. The beauty of a suspension bridge is that the cable works purely in tension, not bending or compression. That's the ideal mode for high-strength steel. The elastic modulus and tensile strength of these wires are engineered so working stresses stay well below the breaking point, even accounting for wind gusts, temperature swings, and traffic surges. During the design phase, engineers model every possible loading scenario. Both lanes completely packed with semi-trucks, sudden braking, seismic effects. The result is an acceptable range of cable stretch and sag within which the bridge remains safe and comfortable for users. Interestingly, despite the system's rigidity, the main cables aren't absolutely stationary. They breathe along with the bridge. When heated on a sunny day, the steel expands and the cable sags slightly. During nighttime cooling, tension increases and sag decreases. In windy weather, you can notice a gentle swaying of the deck. In reality, the cables themselves are also moving, though it's invisible to the eye. It's precisely this living, flexible behavior that allows suspension bridges to handle dynamic loads better than rigid, overly stone-like structures. Excessive rigidity is exactly what led to disasters throughout the history of bridge building, while controlled flexibility allows the dissipation of vibrational energy. A separate critical topic is protecting cables from corrosion. Steel fears moisture and salt spray, especially in coastal regions like San Francisco. If water and aggressive contaminants penetrate inside the cable, reaching each of the tens of thousands of wires, corrosion can invisibly eat away at the cross-section for years until it's too late. That's why immediately after spinning and compacting are complete, cables are sealed. First carefully painted, then periodically recoated. Modern bridges employ additional systems: wrapping with hermetic tape, filling gaps with dried air or nitrogen, and monitoring internal humidity levels. Regular inspections are conducted, including magnetic or ultrasonic non-destructive testing methods that allow engineers to assess the condition of the wires without actually opening up the cable. All of this is done so that a single thread of infrastructure can serve safely for decades. The Golden Gate's cables were designed for a service life of several decades, but thanks to smart maintenance, regular repainting, and monitoring, they're still doing their job today, holding up a main span of over 4,000 feet. If you factor in other suspension bridges around the world, the picture becomes even more impressive. Hundreds of thousands of miles of steel wire strung between riverbanks, bays, and straits, holding millions of cars in the air every single day. Using main cables made from thousands of steel wires is the standard for major suspension bridges, so the Golden Gate isn't alone here. One of its most famous relatives is the George Washington Bridge over the Hudson in New York. It also has two main cables, woven from tens of thousands of steel wires. The total length of all the wire there is measured in thousands of miles, and each cable weighs tens of thousands of tons, just like the Golden Gate. Similar technology was used on the Brooklyn Bridge, though it's older and combines a suspension design with stays. There, the main cables are also made up of a large number of thin wires, woven on-site rather than brought in as pre-made rope. Today's giants are built using the same principle. Take the Akashi Kaikyo Bridge in Japan, one of the longest suspension bridges on Earth. Its main cables? Made from thousands upon thousands of high-strength steel wires. String them all together, and you're looking at tens of thousands of miles of cable. The tension in those cables? Hundreds of thousands of tons. You see the same engineering playbook in China and South Korea, where they've been racing to build massive suspension bridges over bays and wide rivers for the past few decades. Every nuclear reactor on the planet has an emergency brake. Not a button, not a switch. A metal. Drop it into the core, and the chain reaction stops cold. Pull it out too slowly, and you get Chernobyl. The entire world produces just 70 tons of this metal per year. That's one railroad car. One single car, standing between controlled fission and catastrophe. 5 factories make it. Maybe 6, if you count one in China, that nobody talks about openly. Fewer factories than NFL teams. And here's the thing. This same metal is sitting inside your phone right now. Billions of devices, atoms-thin layers. The metal is called hafnium, and nobody told you about it. But before hafnium ends up in a reactor or a chip, it has to be ripped from its chemical twin. That separation is one of the hardest jobs in metallurgy. Hafnium never shows up alone. Nowhere on Earth. Never has. It hides inside zirconium. Every sample of zircon mineral ever pulled from the ground has 1 to 3% hafnium baked into it. Always. No exceptions. Now pay attention to this. Zirconium and hafnium are chemical twins. Same atom size. Same valence. Same behavior in almost every reaction you throw at them. So alike that Mendeleev never spotted hafnium when he built the periodic table. It stayed hidden for over 50 years, until 1922, riding on zirconium's back like a stowaway. Think about that. An element hiding in plain sight for half a century. Separating these two costs a fortune. Not because the chemistry is exotic, because the difference between them is almost nothing. So why bother? One property. One single property where they're total opposites. And that property keeps nuclear reactors from melting down. Zirconium is transparent to neutrons. They fly straight through it like light through glass. That's why nuclear fuel rods are wrapped in zirconium. Hafnium does the exact opposite. It swallows neutrons, 600 times more than zirconium. 600. That makes hafnium the emergency brake of every nuclear reactor. Control rods, the metal plates that slide into the core to kill the chain reaction, made from hafnium. When something goes wrong, hafnium rods drop in. They absorb every neutron in their path. Reaction over. American nuclear submarines run on hafnium control rods. Compact, reliable, no second chances needed. Now here's where the money starts burning. To make nuclear-grade zirconium, every trace of hafnium must come out. To get pure hafnium, it has to be stripped from the zirconium completely. Both processes happen at the same plant. Both are brutal. Both start with sand. A specific mineral pulled from beaches in Australia and Africa. What happens next involves 100 repetitions of the same chemical trick and a column of machines taller than a 3-story building. Raw material, zircon sand. Looks ordinary. Slightly heavier than beach sand. Faint metallic shimmer. It gets processed into zirconium chloride, a powder that acts like salt with an attitude. Sucks moisture from the air so aggressively that workers handle it in climate-controlled dry rooms. The hardest part comes next. Liquid-liquid extraction. Dissolve that chloride in water. Add an organic solvent. The two liquids grab zirconium and hafnium at slightly different rates. Hafnium moves a tiny bit more into the organic layer. Zirconium stays in the water. A tiny bit. That's the problem. One pass does almost nothing, so they repeat it. 50 times. Sometimes 100. 50 separate extraction vessels chained together in a column the size of a warehouse wall. Liquid cycling back and forth for months. The electricity bill alone would make your eyes water. A single solvent leak shuts the whole line down for a week. Picture a 100-step coin sort where heads and tails are almost the same weight. That's what this machine does. And it never stops. After 100 cycles, hafnium comes out as a chloride compound. Still not metal. Turning it into metal requires temperatures that would melt most equipment. Hafnium chloride gets packed into a sealed vessel with chunks of magnesium. Temperature climbs to 1650 degrees Fahrenheit. Magnesium rips the chlorine atoms off hafnium and bonds with them. What's left behind is pure hafnium. But it comes out as a rough, grey, porous mass. They call it hafnium sponge. Looks like pumice stone someone left in a furnace. Pick it up and it feels heavier than it should. That ugly grey sponge costs over $1,000 per kilogram. More per ounce than gold at certain market points. And it's still not ready for a reactor. Only a handful of companies buy it directly. Framatome in France, Westinghouse in the US. Shipments move in sealed containers under strict tracking. Lose a batch in transit, and people in government offices start asking questions. Vacuum arc furnace. Temperature above 4,000 degrees Fahrenheit. Hafnium melts at 4,050. At that heat, it reacts violently with oxygen and nitrogen. Even a breath of air inside the furnace makes the metal brittle and useless. So the chamber is sealed, air pumped out, replaced with argon. No oxygen, no nitrogen, no room for error. First melt produces an ingot. Composition isn't uniform enough, so they melt it again. Sometimes a third time. The final ingot weighs 10 to 20 pounds. Grey, shiny, looks a bit like stainless steel. Think about what it took to get here. 1 ton of sand, 100 extraction cycles, a magnesium reduction at 1650 degrees, 3 passes through a vacuum furnace above 4,000 degrees, all for a 20-pound bar of metal. That bar still has to prove it's clean enough. In a nuclear reactor, almost pure and pure are two completely different things. Nuclear-grade hafnium must contain less than 1% zirconium. Zirconium isn't toxic, it just lets neutrons pass through. If a control rod has 2% instead of 1, it absorbs fewer neutrons. Under normal conditions, nobody notices. During an emergency shutdown, when every neutron counts, that extra percent could mean the rod fails to stop the reaction in time. 1%. That's the line between safe and not safe. Every ingot gets mass spectrometry analysis. Every batch comes with a chemical passport. The buyers don't take the factory's word for it. Government nuclear programs, defense contractors. They run their own tests in independent labs. Zero trust. The cost of a bad batch isn't money. It's a reactor that won't shut down when it needs to. 5 factories on Earth can meet that standard. And now a second industry is pulling on that same tiny supply. Since 2007, hafnium has had a second life. Inside microprocessors. When transistors shrank below 12 nanometers, the old insulating layer stopped working. Too thin. Current leaked straight through like water through a cracked pipe. Hafnium oxide solved that. A few atomic layers hold the charge where silicon can't. Every modern processor contains hafnium. Phones, laptops, data centers. Microscopic amounts, but across billions of devices, it adds up. A second major buyer pulling on a supply that fills 1 railroad car per year. 1 factory down for maintenance can move global prices. 2 offline at once, and both nuclear and semiconductor start making uncomfortable phone calls. There are no hafnium mines. Not one. Every gram ever produced is a byproduct of zirconium processing. If demand for zirconium drops, hafnium supply drops with it, even if demand for hafnium is going up. 2 industries fighting over a metal that only exists because someone else needed its twin. 70 tons a year. 5 factories. A supply chain so thin that losing 2 of them would send shockwaves through nuclear energy and tech at the same time. Next time you pick up your phone, Remember this. Somewhere between the glass and the battery, there are atoms of a metal that doubles as a nuclear reactor's emergency brake, and there's barely enough of it to go around. Next one. A metal they pull from volcanic rock at 3,000 degrees. One country controls 90% of the supply. Imagine, every year, the world produces over 108 million cubic meters of particle board, recycling 16 million tons of wood waste that could have just rotted in landfills or been burned. This isn't just a material, it's a recycling revolution. From old packaging, offcuts, and even used furniture to the sturdy foundation for your cabinets, tables, and shelves. And did you know that 25% of this production is already certified as environmentally friendly? In this video, we'll uncover the secrets of this industrial marvel. From giant chippers that swallow logs to hot presses where resin creates a monolith. Find out how waste is brought back to life in the three-layer sandwich of a perfect board, and why this is the future of sustainable design. Ready for a journey from trash to masterpiece? Don't look away. Every step will mesmerize you. It all begins at a huge raw material yard, where the foundation for the future particle board arrives in a continuous stream. This is a place where the idea of rational resource use is brought to life on an impressive scale. Contrary to popular belief, high-quality commercial timber is almost never used for particle board production. Instead, the production philosophy is to give a second life to wood waste, turning what was previously considered a byproduct into a valuable material. Piles of raw material, reaching tens of feet high, are brought here. The base is technological chips, obtained from low-quality wood that is not suitable for lumber production. A huge share consists of waste from sawmills. Slab wood, which is the side parts of a log with a rounded surface, board offcuts, and thin strips that remain after log cutting. Woodworking waste, such as shavings and sawdust generated at furniture and carpentry factories during planing and milling, is also actively used. A separate and important direction is secondary wood. Old wooden pallets, crates, packaging, and even used furniture, after a thorough cleaning process, get a chance for a new life as part of a particle board. Every batch of incoming raw material undergoes strict incoming inspection, as purity is the key to quality. The first stage of cleaning is the removal of metal inclusions. Powerful electromagnetic separators, capable of pulling a steel bolt from a distance of several inches, sift through the stream of raw material, removing nails, staples, and any other metal fragments that could catastrophically damage the expensive shredding equipment. Next, the raw material passes through screening systems to remove mineral impurities, sand, stones, and other debris that act as an abrasive and quickly dull the cutting tools. If whole logs are used in production, for example, 20 feet long, they must pass through a debarking machine. In a huge rotating drum, or with the help of special cutters, the bark is removed from them. This step is critically important, as bark has a different structure, contains a lot of dirt, and significantly worsens the quality of wood chip bonding, as well as negatively affecting the appearance and strength of the final product. The prepared and cleaned wood begins its journey on a conveyor belt hundreds of feet long, which relentlessly carries it to the first stage of mechanical transformation. It disappears into the steel maw of a giant chipper, an industrial monster the size of a small room, capable of swallowing pieces of wood several feet thick. Inside this machine, with a deafening roar that makes the workshop floor tremble, a massive disc equipped with razor-sharp knives rotates. Rotating at a speed of thousands of revolutions per minute, these knives cut into the wood with incredible ease, turning whole pieces into a stream of uniform chips a few inches in size. But this material, despite its uniformity, is only a semi-finished product. The resulting chips are too large, coarse, and non-uniform in shape to create a quality particle board. Their cubic structure would not allow for the creation of a dense and monolithic structure. Therefore, The next step is a finer and more delicate secondary grinding, which takes place in specialized flakers or mills. It is here, in the hum of high-precision equipment, that the very particle that gave the final product its name is born. At this stage, the geometry of the chip becomes crucial, as it is designed with engineering precision. For the outer, face layers of the particle board, which will be responsible for its appearance and smoothness, very fine, thin, and flat flakes are needed. They are produced in knife ring flakers, which literally shave thin flakes from the chips, resembling flakes only a few hundredths of an inch thick. These flakes, having a large surface area, perfectly bond with the resin and form a flawlessly smooth surface, ready for further processing. In contrast, for the inner, central layer of the board, which is its structural backbone, larger and thicker flakes are used. They create a strong internal frame that gives the particle board its final rigidity, bending strength, and the ability to securely hold fasteners, such as screws and bolts. The resulting chip mass has varying moisture content, which is unacceptable for quality bonding. Therefore, all the chips are sent to one of the most important stages, drying. Usually, huge drum dryers are used for this. The chips are continuously fed into a rotating drum, where they are blown with hot air or flue gases. The process is strictly controlled by automation. The final moisture content of the chips must be in a very narrow range, from 2 to 6%. If the chips are over-dried, they will not be properly saturated with glue. If they remain too moist during hot pressing, the excess water vapor can rupture the board from the inside, forming defects. The dried chips are not uniform in size. To create the correct 3-layer structure of the board, they must be sorted. The chip mass passes through a system of mechanical screens or air separators. Heavier and larger chips, intended for the inner layer, settle first. The lighter and finer fraction for the outer layers flies further. This process allows for obtaining 2 or more streams of chips of different geometries, which will be used to form the sandwich of the future board. Now it's time for the key component that will turn the loose mass of chips into a monolithic board, the binder. Most often, these are synthetic resins, mainly urea formaldehyde or melamine urea formaldehyde. The sorted chips enter special continuous mixers. Inside them, the resin is sprayed through nozzles, creating a glue mist that evenly envelops each particle of wood. The dosage of the resin is critically important and is usually from 6% to 10% of the mass of dry chips. Along with the resin, other components may be added. The resinated chips, now sticky and ready for bonding, are finally ready to become a board. They are transported to a massive forming machine, where a continuous chip mat is born from the scattered particles. It is here that the engineering magic of creating a 3-layer structure takes place. The forming machine is a complex system that sequentially and with high precision sprinkles chips onto a moving conveyor belt. First, it creates a perfectly even bottom layer, using the smallest fraction of chips. Immediately after this, a much thicker middle layer, consisting of large and strong chips, is laid on this base. Finally, the entire mat is covered with another layer of the fine fraction, creating a mirror image of the bottom layer. This carefully designed structure, resembling a sandwich, provides the unique properties of the future board. Its smooth and dense outer layers are ideal for further sanding and laminating, while the strong inner layer gives the board the necessary rigidity and the ability to securely hold fasteners. The formed but still loose mat passes through a pre-press, where it is significantly compacted. This pre-pressing removes excess air from it and gives it a shape convenient for loading into the main press. This is the culmination of the entire technological process. The pre-pressed and cut into fragments of a given length mat is fed into a hot press. This can be either a giant multi-opening press of periodic action, which simultaneously compresses a whole stack of boards, or a modern continuous press of the belt type. Inside the press, the chip mass is simultaneously affected by two powerful factors. Huge pressure, reaching tens of kilograms per square centimeter, compresses the chips, leaving no voids between the particles. At the same time, the press platens, heated to a temperature of 400 degrees Fahrenheit, transfer their heat to the mat. This high temperature activates the resin, launching an irreversible polymerization process. The liquid glue instantly turns into an extremely hard and strong polymer, which permanently glues millions of wood particles together. The time spent in the press depends on the thickness of the board and usually lasts only a few minutes. During this short period, the loose mat turns into a hot, hard, and absolutely monolithic particle board. The hot boards after the press cannot be stacked immediately. They need to be cooled gradually to relieve internal thermal stresses and avoid further deformation or warping. For this, they are placed in special stair or fan coolers, where they are blown with air for several hours until they are completely cooled and their structure is stabilized. The next step is calibration and sanding, which gives the board a marketable appearance. The boards pass through sanding machines with several heads, where wide abrasive belts remove a thin surface layer, bringing the board to a precise specified thickness and creating a perfectly smooth surface. At the final stage, the large technological boards are cut into standard commercial formats, and their edges are trimmed. The finished product undergoes strict quality control, where its density, bending strength, moisture content, surface quality, and dimensional accuracy are checked. Only quality boards are marked and sent to the warehouse. From there, their path lies to furniture factories, where they will be transformed into familiar household items, silently demonstrating the amazing journey from unnecessary chips to a functional and indispensable foundation of our comfort. Your smartphone weighs 5 pounds and holds a charge for 30 minutes. Your laptop's chained to the wall because the battery dies in 20 minutes. Electric cars don't exist. The battery would weigh more than the entire car and only go 50 miles. Cordless power tools, wireless headphones, anything portable, just impossible. All because we never figured out how to mine and refine one soft silvery metal that stores more energy per pound than any other practical battery chemistry. Without this metal, we'd still be stuck with 70s technology. Nickel-cadmium batteries that weigh 10 times more, last 10 times less, and leak toxic heavy metals. Your phone would need a brick-sized battery. Today, we're going inside a facility in Nevada, where this metal is extracted from ancient underground brine, and I'll show you what properties make it irreplaceable and what the world looks like if we have to use something else. The Albemarle lithium facility at Silver Peak, Nevada, sits in a desert valley 190 miles northwest of Las Vegas and has been producing lithium continuously since 1966. 10,000 feet beneath the surface lies a massive geothermal brine reservoir containing dissolved lithium chloride that's been concentrating for millions of years. The facility pumps this brine and processes 6,000 tons of lithium carbonate annually. If lithium had never been discovered, all batteries would use nickel-cadmium or lead-acid chemistry. A lithium-ion battery stores 160 watt-hours per kilogram. Nickel-cadmium stores 40. Lead-acid just 30. To match a modern iPhone battery, you'd need 2.5 pounds of nickel-cadmium instead of 2 ounces. The phone becomes a brick. Mobile computing doesn't exist. The first stage pumps geothermal brine from wells drilled 10,000 feet deep. This brine comes up at 200 degrees Fahrenheit, carrying 300 parts per million of dissolved lithium, along with sodium, potassium, and magnesium. The brine flows into massive evaporation ponds, covering thousands of acres, where the Nevada sun and desert wind do the work. Over 12 to 18 months, the water evaporates, and lithium concentration increases from 300 to 6,000 parts per million. This creates lithium's first critical property. Extreme reactivity makes it the lightest metal that can store electrical charge. Lithium atoms give up electrons more easily than any other practical metal, exactly what you need in a battery anode. Without this, you'd need heavier metals like nickel or cadmium, which means heavier batteries for the same energy. After evaporation, the concentrated brine moves to a chemical plant where it's treated with sodium carbonate to precipitate lithium carbonate as a white powder. This powder is washed, filtered, and dried to 99.5% purity. Lithium carbonate looks like fine white sand, ready to ship to battery manufacturers. Lithium's voltage characteristics become critical here. A lithium-ion cell operates at 3.7 volts. Nickel-cadmium runs at 1.2 volts. To match lithium's voltage, you'd need 3 times as many nickel-cadmium cells wired in series, tripling the weight and complexity. A 6-cell lithium laptop battery would require 18 nickel-cadmium cells. A 1-pound battery pack would weigh 7 pounds, making laptops impossible to carry. Lithium carbonate gets shipped to battery manufacturers, where it's processed into lithium metal or lithium compounds for battery cathodes and anodes. Modern lithium-ion batteries use lithium cobalt oxide or lithium iron phosphate for the cathode and graphite with embedded lithium for the anode. During charging, lithium ions move from the cathode to the anode through the electrolyte. During discharge, they move back, generating current. This reversible movement creates unmatched energy density. A lithium-ion battery handles 1,000 cycles while retaining 80% capacity. Nickel-cadmium manages 500 cycles. Lead-acid gets 300. Without lithium, devices need battery replacement twice as often, generating toxic waste because nickel-cadmium contains poisonous cadmium and lead-acid contains brain-damaging lead. Battery manufacturers shape lithium electrodes into thin sheets and stack them with separators, creating battery cells. Multiple cells connect to form packs for phones, laptops, cars, and tools. Each application demands specific energy density and safety features, but all depend on lithium's unique properties. Lithium's power-to-weight ratio is revolutionary. The Tesla Model 3 has a battery pack weighing 1,000 pounds that stores 75 kilowatt-hours, delivering 300 miles of range. With nickel-cadmium, you'd need 6,000 pounds of batteries to match that energy, but the car weighs only 3,500 pounds total. The battery weighs more than the car. You can't build a practical electric vehicle. Tesla doesn't exist. Electric cars remain a failed experiment from the early 1900s. Every batch of lithium and every battery goes through rigorous safety testing, and there's a specific reason why lithium battery safety standards are so incredibly strict. In 2016, Samsung released the Galaxy Note 7 smartphone with a lithium-ion battery that had a design flaw. The internal structure allowed the positive and negative electrodes to touch under certain conditions, creating a short circuit. Samsung had to recall 2.5 million phones globally. The recall cost them $5.3 billion. Airlines banned the Note 7 on flights. The incident nearly destroyed Samsung's phone business and proved that lithium batteries demand perfect manufacturing with zero tolerance for defects. Today, every lithium battery undergoes crush testing, puncture testing, thermal cycling between -40 and 150 degrees Fahrenheit, overcharging, and internal short-circuit simulation. The rejection rate for lithium battery cells is around 8%. Lithium that's passed all testing gets shipped to electronics manufacturers around the world. The Silver Peak facility produces 6,000 tons annually, but global production is roughly 400,000 tons because demand is massive. Without lithium, portable electronics barely exist. Your phone stays plugged into the wall, like it's the 80s. Laptops are 20-pound luggables with 30-minute battery life. Wireless earbuds, cordless drills, e-bikes, drones, portable medical devices, none of it exists. Anything portable and electronic requires a gas generator or an extension cord. Electric vehicles are impossible. Every automaker tried EVs with lead-acid or nickel metal hydride batteries in the 90s and 2000s. All failed. Maximum range 60 to 80 miles. Batteries died after 2 years. Without lithium-ion, Tesla never gets started. EVs remain a failed technology, and we're stuck with gas cars with no viable alternative. Renewable energy storage doesn't work at practical scale. Solar and wind need massive batteries to store energy when the sun doesn't shine or the wind doesn't blow. Without lithium, these systems would be warehouses full of lead-acid batteries weighing 50 times more, costing 10 times more, needing replacement every 3 years. Grid-scale energy storage is economically impossible. Renewable energy remains tiny because it's too unreliable without storage. Without this lightweight, high-voltage metal, we're stuck in a world where electronics stay plugged into outlets, portable devices don't exist, electric cars are impossible, and renewable energy can't replace fossil fuels. You've seen how brine containing 300 parts per million lithium concentrates through evaporation to 6,000 parts per million. How chemical processing creates 99.5% pure lithium carbonate. How lithium's properties create batteries with 4 times the energy density of alternatives. And why the Galaxy Note 7 proved that lithium production demands absolute precision. If this hooked you, subscribe for more content making modern life possible. Thanks for watching. Picture a single engine as tall as a 4-story building and longer than 2 city buses parked end to end. It weighs 2,300 tons. That's more than 350 full-grown elephants stacked into one machine. One piston inside it is taller than a man. The crankshaft alone weighs 300 tons. And when it runs, it puts out over 107,000 horsepower, turning a propeller bigger than a house. This is the largest engine human beings have ever built, and almost nobody has ever seen one in person. And here's the thing, nobody tells you. This monster turns over slower than the second hand on your watch, and that's exactly why it can move a ship the size of a city block. Watch to the end, because the part that holds the whole thing together is forged in a way only a few factories on Earth can pull off. Start with the scale, because the numbers don't feel real until you stand next to them. The biggest of these engines, the Wärtsilä Sulzer RT Flex 96C, stands almost 44 feet tall and nearly 90 feet long. Walking from one end to the other is about 30 paces, and it weighs 2,300 tons, the same as 11 fully loaded railroad locomotives. Compare that to your car. Yours makes maybe 200 horsepower. This thing makes over 107,000, more than 500 family cars bolted into one block of steel. And it doesn't scream like a race car. It thumps, slow, heavy, deliberate. At full power, it turns just 102 times a minute. Your kitchen blender spins 100 times faster than the most powerful engine on the planet. That's the whole trick. Brute force, almost no speed. So, how do you build something this big? You don't pour it in one piece. Nobody can. The block, the cylinders, the crankshaft, the pistons, every part comes from a different forge, and some are the only ones in the world that can do the job. It starts in the foundry. The bed plate the whole engine sits on gets poured from molten iron at around 2,600 degrees. A single casting can weigh dozens of tons, and it takes a crane just to move the empty sand mold. When the iron pours, it glows white and runs like water. Then it sits, for days, cooling slowly, because if you rush it, the metal cracks from the inside, and a crack you can't see at the factory will tear the engine apart at sea. One flaw, and a ship loses power in the middle of the ocean. Now we get to the part the engineers lose sleep over, the crankshaft. This is the spine of the engine, the steel bar every piston pushes against to turn the propeller. And on the biggest engines, it weighs around 300 tons, all by itself. 300 tons. Heavier than the Statue of Liberty. You can't cast a part like this, because cast metal is brittle, and this shaft takes a beating every second the engine runs. So it has to be forged. They heat a block of solid steel until it glows orange, then a press squeezes it with thousands of tons of force, hammering the grain of the metal into shape so it survives decades of pounding. It comes in sections, each machined to a tolerance finer than a sheet of paper. Only a handful of foundries on Earth can forge a shaft this large. This single part is why these engines can't just be built anywhere. Then there are the pistons, and this is where the size really hits you. The cylinder bore, the hole the piston slides in, measures 38 inches across, just over 3 feet. You could sit inside one. The piston that fills it is taller than most people, and it travels almost 8 feet up and down on every stroke. 8 feet. Most car engines move their pistons 3 or 4 inches. Each time it fires, the pressure inside is enormous, and the temperature climbs past the point where ordinary steel would soften and fail. So the piston crown gets cooled from the inside by oil pumped through channels drilled into the metal. 14 of these cylinders line up down the length of the engine. 14 explosions, firing in sequence, 100 times a minute, for years on end without ever shutting down. Here's a number that should stop you cold. The torque on the crankshaft, the raw twisting force, is over 7.5 million Newton meters. Torque is the muscle that turns the propeller. A strong pickup truck makes maybe 500 Newton meters. This engine makes 15,000 times more. That's the force it takes to spin a propeller the size of a small house through thick seawater while dragging 200,000 tons of steel and cargo behind it. And it does it sipping fuel. These slow-turning giants are the most efficient combustion engines ever made. More than half the energy in the fuel actually goes into moving the ship, while your car wastes most of its fuel as heat. That's why it runs the world's oceans. Now comes assembly, in a hall the size of an aircraft hangar. The bed plate goes down first, leveled to a fraction of a millimeter, because if the foundation is off, every part above it wears out fast. Then the crankshaft is lowered in by overhead crane, 300 tons swinging in the air, guided into its bearings by workers reading hand signals. The cylinder block stacks on top. Then the liners, the pistons, the connecting rods, each craned into place and torqued to spec. A single connecting rod weighs more than a small car. Bolts the size of your forearm get tightened with hydraulic tools, because no human arm could turn them. The build takes months. And when it's done, that engine has well over 250,000 parts inside it, everyone placed by hand. Before it ever touches a ship, the engine has to prove itself. They bolt it to a test bed, hook it to a giant brake that absorbs all that power, and run it. Cold start, slow warm-up, then harder and harder, until it's making full power on the floor. Sensors cover every surface, watching temperature, pressure, vibration, the bend in the crankshaft as it loads up. They run it for hours, at overload, hunting the one tiny problem that won't show on land, but would become a disaster 1,000 miles out at sea. Because once this engine is sealed inside a hull, and the ship sails, there's no pulling it out. It has to run, day and night, for the entire life of the vessel. 20, 30 years. Only after it passes every test does it get torn back down, packed into sections, and shipped to the yard. So, where does all of this go? And why does it matter to you? Onto a container ship. The kind that carries 20,000 steel boxes stacked 9 high above the deck. That engine, dropped into the belly of the hull, is the only thing moving every phone, every car part, every pair of shoes across the ocean to your door. Around 90% of everything traded between countries moves by sea, and almost all of it rides on top of an engine like this. The sneakers on your feet, the coffee in your cup, the screen you're watching this on. Everyone crossed an ocean inside one of these slow, thumping giants, burning heavy fuel oil, turning that propeller 100 times a minute, mile after mile, almost never failing, because failing in the middle of an ocean is not an option. And here's the part that ties it all together. This engine almost never shuts off. From the day it's commissioned, it can run for months at a stretch, only stopping in port. It burns the cheapest, thickest fuel on Earth, a sludge so heavy it has to be heated just to flow through a pipe. And out of that black tar, it pulls more useful work than any engine ever built by hand. 2,300 tons of iron and steel, 14 cylinders, 300 tons of forged crankshaft, all turning slower than your second hand, moving the entire world economy across the water without anyone ever seeing it work. That's the real story of the largest engine on the planet. It hides in the dark at the bottom of a ship, and it never gets the credit. If this changed how you think about the stuff that shows up at your door, hit subscribe, and I'll show you the next machine most people never get to see. Every second globally, over 3 billion gigabytes of data are transmitted. But did you know that all this happens thanks to a thread thinner than a human hair? And that this thread starts with ordinary sand. Not beach sand, but perfectly pure quartz, where there's only one impurity per million parts. To create fiber optic cable that transmits light at a speed exceeding 300,000 kilometers per second, you have to go through a journey involving chemical vapors, sterile laboratories, a 2,500-degree furnace, and lasers that monitor every microcrack. This process looks more like manufacturing a spaceship than a cable, but it is the foundation of the internet you are using right now. To create a thread capable of transmitting light at a speed exceeding 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, meaning in 1 million parts, there's only 1 part of impurities. Imagine this: in every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical, because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop. And all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense, solid rod. And this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break, cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire. So the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this, without a single break, without a single scratch. Because even a micro crack, and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe resistant to ultraviolet light, moisture, rodents, temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation. Every year, millions of tons of metal waste get recycled worldwide, but only at the very end of this massive process does a substance emerge that's heavier than almost anything you've ever held in your hands. Picture a metal where a tiny piece weighs as much as a brick, and extracting it is more like hunting ghosts through fire and acid. Today, we're stepping inside a facility where one of the rarest and most mysterious metals on the planet is born from dirty sludge: osmium. But the most shocking part isn't its weight. It's what you have to go through to get even one small bar. And trust me, if you stick around until the end of this video, you'll learn a fact about this metal that literally breaks logic and makes you question the laws of physics. We're now entering the primary processing facility for platinum sludges. Everything around here is humming, steam's bursting out from under valves, and the workers look like they're gearing up for a flight to another galaxy based on the sheer amount of protective gear they're wearing. And that's no surprise. Osmium is basically the heavyweight champion of the periodic table, and it doesn't tolerate amateurs. It's twice as dense as lead. Just think about that for a second. If you grab a cube of this metal with sides only 4 inches long, it'll weigh nearly 22 pounds. That's like trying to pick up a full-grown cat that's compressed itself down to the size of a matchbox. The process of extracting osmium is a real adventure for anyone who loves complex flowcharts and intellectual challenges. This metal doesn't just lie around in proud nuggets deep in the earth, waiting for some lucky prospector to pick it up and slip it into their pocket. Nope, it's way trickier than that, and hides itself in the residues left over from the industrial purification of copper and nickel. Picture a whole mountain of rock that's already been processed, squeezed for everything possible, and only at the very end, in the dirty sludge, this heavyweight remains. You and I walk past massive vats where all hell breaks loose because the metal mixture gets hit with aggressive chlorine and insanely high temperatures. It looks like a set from a movie about the future, where humanity learned to extract value from dust. The work starts with anode slime. That's the sediment left over after electrolysis. To get to the osmium, specialists have to literally dismantle the molecular structure of this waste. First, the slime gets treated with acids to wash out the more cooperative metals. When it's our hero's turn, thermal processing kicks in. Temperatures here reach thousands of degrees Fahrenheit. This isn't just heating, it's total transformation of matter under the watch of dozens of sensors. When the mixture hits the reactors with chlorine, the most critical stage begins. Osmium reacts and transforms into a volatile compound. This gas needs to be captured with pharmaceutical precision. The slightest error in pressure or temperature, and the precious metal simply flies up the stack, leaving behind nothing but a foul smell. Special absorption towers step by step pull the gas in, converting it into a solution. It's like hunting a ghost, except instead of traps, you're using complex chemical filters. Next, the solution goes through several more purification stages until finally a precipitate appears, pure osmium salt. But that's still not the end of the road. This salt gets roasted again in a stream of hydrogen to produce that same dark blue powder. Every pound of this powder, that's the result of hundreds of workers and massive machines grinding away. Looking at these vats, you realize that osmium extraction isn't just metallurgy. It's the pinnacle of engineering genius, where every move costs thousands of dollars. This is work for the patient and the bold, because this metal doesn't forgive mistakes, but it rewards those who make it through all these fiery and chemical obstacles with its otherworldly strength. To extract it, you need to convert it into osmium tetroxide. And this is where the fun really begins, because this gas smells like someone decided to mix bleach with rotten radish and set it all on fire in a closed room. The metal's name actually comes from the Greek word meaning smell, and trust me, the Greeks knew what they were talking about. We move on to the separation laboratory. Here reigns an atmosphere of sterility that contrasts with the dirty rumble of the previous workshop. Scientists in white coats manipulate glass tubes and retorts. The whole process looks like a very expensive and dangerous cooking show. They extract osmium as a fine, dark blue powder. This powder looks beautiful, but it's incredibly treacherous. If you heat it in open air, it instantly becomes a toxic gas that can ruin not just your day, but your health for years to come. So airtightness is everything here. Look at these furnaces. They operate at temperatures that are hard to fathom, over 5,000 degrees Fahrenheit. That's way hotter than the surface of some stars. Because osmium has an incredibly high melting point, you can't just melt it in a bucket and pour it into molds. They use powder metallurgy methods here. The powder gets pressed under gigantic pressure, then sintered in a vacuum. What you get is like a metal sandwich that then becomes a monolith. It's fascinating to watch them try to cut this metal. Regular saws and drills are useless here. They just dull or snap like they're made of chocolate. Osmium is so hard and brittle at the same time that you can only work with it using lasers or supersonic water jets with added abrasives. It's a real challenge for engineers. Every disc or sphere produced costs a small fortune, because making a single part burns as much energy as a small town uses over a weekend. Why even bother with such a finicky material, you might ask? Well, besides looking like a chunk of frozen blue sky, it's incredibly wear resistant. It's used where you need something eternal, in high voltage switch contacts or in the tips of very expensive fountain pens used to sign peace treaties. This is one of those cases where quality justifies every cent spent and every whiff of that weird smell of ozone and chemistry. I'm standing next to a finished ingot. It's small, about the size of my palm, but when I try to move it, my muscles tense up like I'm pushing a small car. This little guy weighs about 35 pounds. You can't capture this feeling through a camera. It violates every law of logic we're used to in everyday life. You expect lightness, and you get a gravitational punch to your arms. Now we're moving into the packaging zone. Even here, everything's serious. Every gram is accounted for. Every ingot has its own certificate and number. This isn't the kind of metal you accidentally forget in your work jacket pocket. Its market price swings so wildly that investors sometimes drink more sedatives than coffee. But demand for this blue shimmer keeps growing because the world's getting more technological, and osmium, it's exactly the ingredient that makes modern electronics reliable. You know what struck me most at this plant? It's the people. They talk about this metal like it's a living creature with a really bad temper, one they've learned to respect and tame just a little. There's no room for rushing here. Every move is calculated to the inch. Every second in the furnace is accounted for. This isn't just manufacturing. It's a battle of human intellect against the physical limits of matter. We're wrapping up our tour at the finished product display. Here you'll find small parts that'll soon ship all over the world. Some will end up in spacecraft, others will become part of medical devices. And every time you hear about something incredibly strong and durable, remember this blue, smelly, and impossibly heavy metal. Hope you enjoyed this walk along the edge of the periodic table. It was tough in every sense of the word. Don't forget, the world around us is way more interesting than it seems at first glance, especially if you peek behind the fence of a big factory. It was fun showing you this metallic extreme. Until next time at new facilities, where we'll definitely find something else that'll make your eyebrows shoot straight up in surprise. Did you enjoy this format? Maybe you'd like me to prepare a detailed script about manufacturing another rare metal, or talk about the logistics of moving these heavy ingots around. What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead built aqueducts, adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron, or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water-repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms. That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid. Every year, over 80,000 wind turbines are installed worldwide. But few people know that each one hides a true engineering masterpiece inside. A blade over 300 feet long that can withstand hurricane-force winds and operate for decades. How do you create a structure so light it can be lifted by a crane, yet so strong it won't break even at rotational speeds exceeding 180 miles per hour? From glass and carbon fiber to vacuum resin infusion, the process of manufacturing wind turbine blades resembles precision surgery on a spacecraft scale. Stick around till the end, and you'll discover why these giant wings have become the symbol of a new energy revolution. Modern megawatt-class turbine blades range from 196 feet to 262 feet in length, and for offshore projects can exceed 360 feet. Why such size? A wind generator's power output is directly proportional to the square of blade length. A longer blade captures a larger wind area, increasing efficiency and, consequently, project profitability. However, with increasing size comes a cubic increase in mass. If you simply scale up a blade, its weight becomes unacceptable and gravitational and inertial loads become destructive. So the key challenge is maintaining low weight with colossal strength. To solve the weight problem, American manufacturers have almost completely abandoned traditional metals in favor of advanced composite materials. Fiberglass is the primary material. It's relatively cheap, strong, has excellent fatigue resistance, and provides necessary stiffness. Fiberglass cloth forms the outer shell and most of the internal structure. For the longest and most powerful blades, carbon fiber is indispensable. It's twice as light and several times stronger than fiberglass. It's strategically used in the most heavily loaded zones, in the longitudinal beams called spar caps that run the entire length of the blade and are responsible for its structural integrity. The fibers are impregnated with epoxy or polyester resins, which, when cured, bind the fibers into a single, extremely strong monolith. This is the heart of the process. To create sandwich structures that give the blade volume and stiffness at minimum weight, analogous to honeycombs, lightweight core materials are used, such as balsa wood or specialized polymer foams. Manufacturing a blade is a multi-month process that requires surgical precision, even though it takes place in massive facilities. The first step is creating a giant mold, or matrix. This typically consists of two massive halves made of durable composites or steel. The mold must perfectly replicate the complex aerodynamic profile of the future blade. Profile accuracy is critical for aerodynamic efficiency and noise minimization. Spar caps are essentially the blade's spine. At this stage, strips of carbon fiber or fiberglass are laid down. If the blade is very large, this process is often fully automated. Robotic systems precisely lay fiber layers into special grooves in the mold. This part is the thickest and bears the main bending loads. The next step is laying fiberglass layers that form the blade's outer shell, as well as core material blocks. Fibers are typically laid by hand by experienced technicians, or using automated fiber placement to ensure proper fiber orientation that will resist predicted loads. After laying all the dry layers, the mold is closed and a deep vacuum is created inside. Resin, epoxy, or polyester is introduced into the mold, and vacuum pressure uniformly and completely impregnates all the fibers, displacing air and ensuring maximum density and strength. This process allows manufacturing large, nearly void-free structures with precisely controlled fiber-to-resin ratios. The resin-filled blade is placed in special ovens or left in the mold under climate-controlled conditions. Heat initiates the polymerization process, during which liquid resin transforms into a solid, strong polymer. This process is lengthy and requires constant temperature control along the entire blade length to avoid internal stresses. After curing, the blades are removed from the mold. The two blade halves, upper and lower, are joined together using special adhesive and additional composite layers. This is one of the most complex stages as it requires perfect alignment over dozens of feet. The root section is where the blade attaches to the turbine nacelle. Powerful steel or composite bushings are embedded here that will withstand enormous loads during rotation and transmit torque. After assembly, the blade is sanded and then coated with special protective coatings. These coatings, particularly on the leading edge, are vital for protecting composite material from erosion caused by rain, hail, dust, and insects, which act like sandblasting at high blade tip speeds. American manufacturers like GE Renewable Energy and TPI Composites pay special attention to quality and innovation to guarantee blade reliability for 20 or even 25 years of operation. No blade leaves the factory without thorough inspection. Since internal defects like air pockets or poor resin impregnation can lead to catastrophic failure. Ultrasonic scanning detects internal defects, voids, and composite delamination. Thermography measures thermal signatures to identify areas with varying density, such as defective bonding. Each new blade model undergoes extreme testing in specialized laboratories. The blade is bent to its strength limit, simulating the strongest wind loads and loads from its own weight to ensure it won't break. Then the blade is forcibly bent forward and backward, up and down millions of times, simulating decades of operation to test material fatigue resistance. After manufacturing comes another engineering challenge: logistics. Transporting a blade over 260 feet from the factory, often located in interior US states, to the installation site requires special low-bed semi-trailers that can rotate the blade around corners and lift it to avoid collisions with infrastructure. It's a unique logistical dance that often requires temporary road closures. Transporting blades is a logistical nightmare. Blade length can easily exceed the wingspan of a Boeing 747. To transport such structures on US roads, special extended semi-trailers are used that can lift, rotate, and tilt the blade at intersections and in mountains. This requires temporary road closures, removal of road signs, and even traffic lights. The US continues investing in developing even longer, lighter, and stronger blades, researching thermoplastic materials for better recyclability, and segmented designs to simplify logistics. This ensures that the engineering marvel born in factories will remain a key element in achieving energy security and sustainability. Some blades, especially older ones that have already served their term, instead of being recycled, are buried in specialized landfills in sparsely populated states like Wyoming. Due to their volume and composite material, fiberglass that doesn't decompose, they can occupy significant areas, becoming museums of green energy. The tips of the longest blades can reach rotational speeds of 180 miles per hour. Though they don't exceed the speed of sound, this requires the blade tip to be perfectly designed and protected from erosion. An ordinary raindrop hitting the blade at such speed has destructive force similar to sandblasting. This forces manufacturers to develop high-tech but expensive protective coatings for blade leading edges. Engineers in the US are developing smart blades that can change their shape or have segmented tips. This allows the turbine to adapt to changing wind speeds and thus increase efficiency and reduce loads. Picture a liquid that goes through at least 10 different transformations before it ends up in the tank of a truck, tractor, or generator. It's boiled, compressed, broken down into molecules, reassembled, cleaned with hydrogen, and tested dozens of times. All of this so an engine can run for hours under load, in scorching heat and freezing cold, without failures or surprises. Diesel fuel seems ordinary, but it's actually one of the most complex products of modern industry, where behind every gallon stands engineering, temperature, and cold calculation. Diesel fuel doesn't just appear from crude oil, like gasoline from a pump. It's the product of a long, hot, and highly controlled chain of processes, where crude oil is gradually transformed from a dark, heavy liquid into a precisely defined mixture of molecules capable of running reliably in an engine. Everything starts with oil, but then it's literally broken down into components, sorted, cleaned, and reassembled, this time in the right form. Crude oil begins its journey far from the refinery, at oil fields, where it's lifted from the Earth's depths through wells. Along with the oil, water, gas, sand, and small rock particles come to the surface. So right at the extraction site, it's partially settled and the largest impurities are separated out. Once it's out of the ground, the oil hits the road. Most of the time, that means pipelines, continuously pumping millions of tons of liquid across hundreds, even thousands of miles. Where there are no pipes, tankers or rail cars take over. Either way, by the time the oil reaches the refinery, it's still far from ready. Before processing can begin, the crude has to be prepped. It almost always contains water, dissolved salts, and solid particles. Leave those in, and they'll wreck the equipment fast. Salts cause corrosion, water messes with stable heating, and solids wear down pumps and pipes. So the oil gets heated and run through desalting and dehydration units. There, it's mixed with fresh water to wash out the salts, then an electric field forces the water to separate and settle. After that, the crude is much cleaner, and a lot safer for what comes next. The prepared crude oil enters the refinery's main unit, the atmospheric distillation column. This is a tall metal tower, like a multi-story building, with dozens of horizontal trays or packing material inside. The column maintains a constant temperature difference. It's super hot at the bottom, and the higher you go, the cooler it gets. The oil is first heated intensely in furnaces, usually to around 660 degrees Fahrenheit, and then injected into the middle of the column in this hot state. Once inside, the oil starts behaving completely differently than it did in the pipeline. It partially vaporizes, creating a mixture of vapor and liquid. Lighter components with lower boiling points quickly turn to vapor and rise upward. Heavier fractions stay lower or flow all the way down to the bottom. Each level of the column corresponds to its own temperature range, so the vapors condense exactly where they're comfortable. As a result of this process, crude oil is essentially taken apart
where it
into its
remains
components.
hottest, settle
The lightest
lubricating
fractions
oils and
collect at
heavy
the top,
residues.
medium ones below, and the heavy residues remain at the very bottom. Everything happens without chemical reactions. The molecules don't break down or change. They simply separate based on physical properties. It's from this point that the real life of crude oil begins as raw material for fuel, lubricants, and dozens of other products, because each fraction obtained will follow its own technological pathway. This is where diesel fraction first appears. It's heavier than gasoline and kerosene, so it condenses lower down, but it's still light enough to be a liquid fuel. This isn't finished diesel fuel yet, just a halfway point, gas oil. It packs a lot of useful energy, but also plenty of sulfur, nitrogen compounds, and unstable molecules that engines hate. The gas oil that comes out of crude distillation is still miles away from the diesel fuel you pump into your tank. It looks similar, sure, but its makeup is dirty by modern standards. It contains sulfur, nitrogen compounds, traces of metals, and unstable hydrocarbon chains that oxidize easily and form carbon deposits. If you fed this stuff straight into an engine, it would quickly destroy the injectors, catalytic converters, and exhaust cleaning systems. That's exactly why gas oil has to go through a hydro-treating stage. At this stage, the fuel gets channeled into special reactors where they create extremely harsh conditions. Temperature there typically hits several hundred degrees, and pressure runs dozens of times higher than atmospheric. Hydrogen gets fed into the gas oil, and this mixture passes through a catalyst bed. The catalyst doesn't get consumed in the process, but it's what forces the chemical reactions to go fast and in the right direction. Without it, purification would either be way too slow or just flat out impossible on an industrial scale. When the gas oil contacts the hydrogen, a series of reactions kicks off. Sulfur-containing compounds break down, and the sulfur converts into hydrogen sulfide, a gas that's easy to separate from the fuel. Nitrogen compounds transform into ammonia, which also gets removed from the stream. At the same time, hydrogen heals unstable molecules. Double bonds get saturated, and fragile structures rearrange into more stable ones. As a result, the fuel becomes chemically calmer, oxidizes less during storage, and behaves better during combustion. After the reactor, the gas oil is cooled and sent to separation units. There, gaseous products, hydrogen sulfide, ammonia, excess hydrogen, are separated from the liquid fuel. Hydrogen is usually recycled back into the process, while harmful gases are sent for further processing or neutralization. It's thanks to this stage that sulfur content in diesel fuel drops by tens or even hundreds of times, down to levels that meet modern environmental standards. The importance of hydrotreatment can't be overstated. It doesn't just cut harmful emissions, it directly impacts engine life. Cleaner fuel puts less wear on fuel injection systems, doesn't poison catalytic converters and particulate filters, burns more consistently, and keeps the engine running predictably. This is really the stage where gas oil stops being a semi-raw material and starts becoming actual diesel fuel suitable for 21st century machinery. But the process doesn't end there. Some diesel components don't even come from primary distillation. Heavy petroleum residues go through vacuum distillation, where reduced pressure extracts even more useful fractions. And if that's still not enough, cracking enters the picture. A process where large, lazy molecules are literally broken down into smaller ones. Hydrocracking is especially critical for diesel because it produces fuel with better combustion characteristics, a higher cetane number, and fewer impurities. After all these stages, different diesel components get blended together. This isn't some random pouring from one barrel to another. It's precise recipe-based mixing. Engineers dial in the proportions so the fuel meets standards. Good ignition, no thickening in the cold, minimal smoke, and no damage to the fuel system. At this stage, they add additives, tiny amounts, but with big impact. They improve lubrication properties, protect against corrosion, reduce foaming, and help the engine start up in winter. Seasonality is a whole different story. Summer diesel is thicker and more stable in warm temperatures. Winter diesel undergoes additional processing. Components that could crystallize in the cold are removed or modified. Otherwise, at 14 degrees Fahrenheit, the fuel starts turning into a cloudy sludge that clogs the filters. For extremely cold regions, they make Arctic diesel, lighter, pricier, and way more complex to produce. Once the fuel's ready, it's stored in tanks, then shipped to fuel depots, and finally to gas stations. But even along that route, it can still be tested, filtered, and adjusted. Diesel isn't a product where you can afford close enough. One small mistake at the refinery can turn into widespread equipment failures. Without this resource, half of humanity would starve, and 99% of people have never even heard of it. I'm standing 2,300 feet underground in a mine that rarely lets cameras inside. Every single day, they set off explosives down here, and the rock is so brittle that one mistake, and the tunnel disappears along with everyone in it in mere seconds. This is potash. Only a handful of facilities worldwide control its extraction, and today, one of them opened its doors to us. To get 1 ton of final product, you need to process 4 tons of raw ore. And how exactly that happens, and what these giants hide behind their metal gates, you'll see by the end of this video. Where do you find it? Deep underground. Very deep. We're talking depths ranging from 1,300 feet to 3,000 feet, sometimes more. It's like descending to the bottom of the Grand Canyon, then going down that same distance again. But how did it end up in Earth's depths? To understand that, we need to take a journey through time, hundreds of millions of years back. In those distant times, where modern potassium salt deposits exist today, there were massive inland seas and ocean bays. These seas were shallow and existed in extremely hot climates, similar to deserts. In these enormous bodies of water, the water constantly evaporated under the scorching sun. When water evaporated, the minerals dissolved in it, like common salt and, well, potash, started settling on the bottom. Think of it like a cup of really salty water you left out in the sun. The water disappears, but the salt stays behind. But on the scale of entire seas, this process took millions of years. Layers of these minerals piled up one after another, forming massive deposits. Eventually, these ancient seas dried up completely, and other rocks accumulated over the salt deposits: clay, sand, limestone. Millions of years of Earth's tectonic activity, continental drift, mountain building, buried these salt layers even deeper below the surface. That's why we find them at depths of thousands of feet. The potash mine itself is a massive, sprawling system of tunnels, stretching for tens, even hundreds of miles. It's an underground city where hundreds of people and giant machines operate. The temperature here is constant, around 75 degrees Fahrenheit, but humidity can be pretty high. And this is where the real challenges and risks begin. These rocks containing potash are called sylvanite. They're brittle, very brittle. One wrong move, one miscalculation, and a collapse can happen. This isn't the kind of work where you can let your guard down. Every miner, every engineer knows the price of a mistake. These are high stakes, with human lives and multi-million-dollar investments on the line. How do they extract potassium? First, massive drilling rigs create blast holes, small openings in the rock. Then they load them with explosives. Yes, actual explosives. And here come more risks. Calculating the amount of explosive, where to place it, timing the detonation. All of this demands tremendous experience and precision. The blast hits, a deep rumble, and tons of rock come crashing down. After the explosion, another set of giants enters the picture. Mining machines. These are massive pieces of equipment that look more like tanks with enormous cutting tools. Their job? Collect the blasted rock and load it onto conveyors. Each machine weighs dozens of tons and costs millions of dollars. They run non-stop, slicing through rock and breaking it into smaller chunks. It's incredibly dusty work, which is why ventilation in the mine is a matter of life and death. A constant flow of fresh air keeps workers safe and maintains visibility. And even with that, everything gets coated in a layer of dust. After traveling hundreds, even thousands of feet underground, the potash concentrate, a mixture of potash salt, common salt, and clay, reaches the surface. And this is where the second, equally complex and fascinating part begins: processing. This isn't some dirty mine anymore. It's a massive, roaring plant where chemical processes bubble and boil. Separating the potassium from all the other junk? That's one hell of a challenge. First step, crushing. Giant crushers turn large chunks of rock into tiny bits. You need this so the next processes can work the material more efficiently. Massive hammers that could demolish a car crush rock here just as easily. You could watch this for hours. Mountains of rock transforming into sand. Next up, the crushed material gets mixed with water. Yep, just water. This is called slurry. This slurry passes through special hydrocyclones, these massive cone-shaped machines that use centrifugal force to separate heavier particles from lighter ones. It's like a spin cycle in a washing machine, but for minerals. This gets rid of some of the clay and other light impurities. And here's where it gets really interesting: flotation. This is the heart of the potash enrichment process. Basically, we make potassium salt float while regular salt sinks. Sounds weird, right? But it works. Special reagents are added to large vats of slurry. These are chemicals that stick to the potassium salt, making it hydrophobic, meaning it repels water. Then air is pumped through this mixture, creating millions of tiny bubbles. The potassium salt, which now hates water, sticks to these bubbles and rises to the surface as foam. Regular salt stays at the bottom. This foam that's risen to the surface, that's our valuable potash concentrate. It gets collected, dewatered, and then dried. Drying happens in massive rotating kilns or dryers, where temperatures can hit several hundred degrees Fahrenheit. This removes all the moisture and gives us a pure, dry product. And right here, we've got our final product, potash, ready to be packaged and shipped to farmers around the world. But the process doesn't end there. Because it's not just about extracting potassium, it's about doing it as efficiently and safely as possible. The water used in the flotation process gets cleaned and cycled back into production. The waste left after separating out the potassium? That's just regular salt and clay. They get disposed of responsibly. At some facilities, that regular salt can even be reused. For example, spreading on roads in winter. From 1 ton of ore, we get only about 25% pure potash salt. That means to produce 1 ton of final product, you need to process 4 tons of ore. Picture this. To meet the needs of, say, an entire country in potassium fertilizers, millions of tons of rock must be processed every single year. We're talking massive volumes of work requiring enormous investments in equipment, technology, and safety. Why is this so expensive? And why are there only a handful of facilities in the world doing this? First, investment. Building a mine and plant like this can cost billions of dollars. This isn't something you build in your garage. Second, incredibly complex engineering. We're talking extraction at enormous depths, working with brittle rock formations, precise chemical processes. Third, safety. Every step in this operation involves risks, from mine collapses to handling chemicals at the plant. Companies spend millions training personnel on modern equipment and safety systems. And finally, it's a rare resource. Potash salt isn't found everywhere, and the places where it exists, these are genuine treasures. Did you appreciate this journey into the world of potassium? We've seen how this valuable resource is extracted from deep within the earth, how it's processed, and how it reaches our fields, helping us grow food. This is a story about engineering excellence, about massive machines, about people working in incredibly challenging conditions, and about a vital element without which the modern world would be completely different. And from you, a subscription. Without this unassuming rock, often mistaken for ordinary dark pebbles or heavy chunks of granite, modern electronics would instantly collapse into a pile of useless plastic and silicon. Tin ore, or more precisely its primary mineral, cassiterite, is the hidden foundation holding up our entire digital world. When we talk about high-tech, we name-drop gold or complex semiconductors, but this is the invisible glue binding billions of microscopic components into a single working system. Tin's journey begins deep in the planet's crust, where for millions of years, metal-rich solutions seeped into fractures in the earth, forming deposits that today drive the pace of human progress. Cassiterite, often called tinstone, has an incredible density and a distinctive diamond-like luster when fractured, though on the outside, it can look like ordinary brown or black rock. Mining this ore demands massive effort and specialized knowledge. The world's major reserves are concentrated in what's called the Tin Belt, stretching through Southeast Asia, China, Latin America, and Africa. The scale of extraction is staggering in its variety, from colossal open-pit mines and underground shafts to dredging operations on the ocean shelf. For example, off the coast of Indonesia, giant floating dredge factories pull up thousands of tons of tin-bearing sand from the seafloor, sifting it through complex filter systems to separate out the heavy ore particles. The process of transforming rock into pure metal is long and exhausting. Since tin content in ore is now low, the rock first undergoes multi-stage enrichment. It's crushed, washed, and separated using gravity methods that exploit cassiterite's high specific gravity. After obtaining the concentrate, the smelting stage begins in a furnace at around 2,200 degrees Fahrenheit. Here, under the influence of reducing agents, tin separates from oxygen and other impurities, transforming into a liquid silvery metal. But for the electronics industry's needs, this purity isn't enough. The metal goes through a series of refining processes to eliminate the tiniest traces of iron, copper, arsenic, or antimony. Only after this does it become the material we see in the form of solder. Solder. That's the main use for tin in the modern world. It's not just some auxiliary material. It's a critically important component of any electronic device. Previously, soldering used an alloy of tin with lead, but due to environmental requirements and health safety concerns, the world switched to lead-free technologies. Today, the latest circuit boards are joined using alloys where tin makes up 95 or even 99%. Every smartphone, laptop, control unit in cars, or satellite onboard computer contains several thousand soldered connections. Without tin's ability to wet the surfaces of other metals and create reliable electrical contact at low temperatures, mass production of electronics would be impossible. Factories that produce modern electronics operate with incredible precision, and that's where a key tool comes into play. In surface mount assembly shops, specialized machines deposit solder paste through stencils onto circuit boards with accuracy down to the micron. Then the board passes through reflow ovens, where the paste transforms into solid metallic connections. It's an automated process where every second and every milligram of metal matters. If the tin contains even minor foreign impurities, it can lead to microcracks or tin whiskers. thin thread-like crystals that grow from the solder and can cause short circuits. That's exactly why quality requirements for tin ore and purification methods keep getting stricter. The impact of tin on urban development and global energy is hard to overstate. Sure, we don't build house frames from this stuff, but it's in every lighting control system, every elevator, every safety sensor. The growth of smart cities relies entirely on billions of sensors and controllers, each one held together by tin solder. This makes it a critical strategic resource, with entire regions shaping their economic policy around the battle for control over its deposits. Countries with major cassiterite reserves become key players in the high-tech supply chain. But tin ore extraction comes with serious challenges. Deep open pits and seabed dredging reshape ecosystems, demanding strict reclamation standards. Responsible companies try to minimize environmental impact by restoring forests and cleaning water used in the refinement process. At the same time, recycling is playing a bigger role. Tin is a metal that can be cycled back infinitely. Recycling old circuit boards keeps the metal's high purity with way less energy than mining it from ore. This creates a closed-loop economy, where yesterday's shattered screen becomes the source material for a new device. Interesting fact, tin's been used for millennia. When it combined with copper to create bronze, it gave an entire era of human history its name. Back then, tin was hunted down as aggressively as we hunt for oil or gas today. But while ancient people made swords and cookware with it, today it's become a tool for transmitting information. That's the evolution of this metal's role. From the brute force of bronze weapons to the refined precision of a silicon chip, where tin provides the pathway for electrons to flow. The stone once prized for its ability to make copper hard is now valued for its malleability and conductivity in the micro-world. Technological progress demands ever-increasing quantities of this metal. The growth of renewable energy, solar panels, and electric vehicles creates additional demand. Each photovoltaic panel requires tin connections to harvest the sun's energy. Electric vehicles contain significantly more electronic components than internal combustion engine cars, making this element essential in the fight for climate neutrality. Thus, ancient cassiterite becomes fuel for the green revolution. It's crucial to understand that tin deposits are distributed extremely unevenly across the planet. This creates certain risks for global production stability. Any disruptions in ore supply from major mining regions instantly impact consumer technology worldwide. This pushes scientists to search for new methods of enriching even low-grade ores, as well as developing technology for extraction from deeper horizons. Every foot of new mine shaft, or every mile of surveyed deposit, is a guarantee that factories keep producing new devices, and the planet's digital network continues to expand. The transformation of tin from mountain rock to solder on a circuit board is an example of how humanity has learned to harness the special properties of materials to achieve remarkable results. It's about tin's ability to be the connecting link. When we look at a chunk of tin ore, we see not just a mineral, but the potential for millions of conversations, terabytes of transmitted data, and the operation of complex mechanisms that ensure our comfort. Tin remains a humble yet irreplaceable hero of the industrial stage, working where no one sees it, at the very heart of machines. Production chains that begin in quarries and end in the clean rooms of high-tech factories are testament to our global interdependence. Tin isn't just a detail on a circuit board, it's the backbone of economies across continents. The continuous flow of ore, concentrate, and finished metal is the circulatory system of industry. Every ton of cassiterite pulled from the earth passes through the hands of thousands of specialists before becoming part of our global information infrastructure. And as we move toward even greater automation and digitization, the role of this stone will only grow, proving that great achievements often start with very small but critically important details. So, tin ore is the real key to modernity. It teaches us to value resources that seem invisible, but without them, the world we know would cease to exist. This is a story about how nature gives us materials, and human ingenuity finds the perfect use for them, transforming heavy ore into the lightness of wireless communication and the speed of data processing. Every grain of cassiterite carries its contribution to global development, remaining an eternal reminder that high technology has its roots in the work of the earth, a stone-born origin. From dark depths to gleaming device cases, the journey of tin is the journey of progress itself. 70% of the plastic you toss in the recycling bin ends up straight in a landfill. Not because you're doing something wrong, but because traditional recycling only wants clean, single-type plastic. Everything else, dirty packaging, films, toys, shoe soles, not its problem. But there's a technology that takes any dirty, mixed plastic and turns it back into oil. No burning, no oxygen. I just visited one of only 25 facilities like this in the entire world, and I'm going to break down exactly how it works. From a pile of trash to a barrel of synthetic oil. Plus, one number from the director that makes it crystal clear. Even this is just a drop in the ocean. Regular plastic recycling, the kind you know from those triangle bins, it's super picky. It wants plastic to be one type, clean, no caps, no labels, no food residue. Plastic bottles, separate. Polyethylene, separate. Polystyrene, they often refuse to take it at all. And anything that doesn't meet these criteria, which is roughly 70% of all plastic that ends up in the trash, goes straight to the landfill, or gets burned. All that dirty food plastic, multi-layer chip bags, toys, shoe soles, films, traditional recycling doesn't want them. And that's where a different game begins. What they do at this facility is called chemical recycling, or plastic pyrolysis. And the principle is so simple, at first you don't even believe it. They take plastic and heat it without oxygen to temperatures between 550 and 900 degrees Fahrenheit. At that temperature, the long polymer chains. And plastic, if we're being brief, is just very long chemical chains, break apart into short fragments. These fragments escape as vapor, enter a condenser, cool down, and turn into liquid. This liquid is pyrolysis oil, or synthetic crude oil. The exact same product that's the starting point for making plastic, gasoline, chemicals. The circle is complete. But the gap between theory and what happens here in practice? Wide as Texas. First problem, raw materials. The plant processes anywhere from 150 to 200 tons of mixed plastic every single day. I saw this pile. It looks like where all your plastic bags, disposable lids, and thermos caps go to die. Before any of this hits the reactor, it goes through sorting, cameras, magnets, air separators. Metal has to come out completely because it just won't break down in the reactor and it clogs the equipment. Chlorinated plastics, for example, have to be separated out because when heated, they release hydrogen chloride, which literally eats the reactor from the inside. One poorly sorted container can shut down the entire line for days and cost the plant tens of thousands of dollars in repairs. After sorting, the plastic gets cut into pieces roughly 1 inch by 1 inch. This ensures even heating in the reactor. The shredders here are the size of a bus and chew through everything with a sound that makes you want to jam in earplugs and drive home. Then these pieces get fed into the reactor by an auger conveyor. The reactor, that's the key piece, and all the complexity revolves around it. It's a massive steel cylinder. This facility has 6 of them, each as tall as a 3-story building. And inside, a complete absence of oxygen is maintained. This is critical. If oxygen gets in at these temperatures, you won't get pyrolysis, you'll get ordinary combustion. Basically, a fire inside. That's why before feeding in the plastic, the system is purged with nitrogen, replacing the air with an inert gas. Oxygen sensors are mounted on every flange, and if the level rises above 0.5%, the line shuts down automatically. At 750 degrees Fahrenheit, polymer chains start breaking apart. Polyethylene, polypropylene, polystyrene, they all have different cracking temperatures, different reaction rates, different product yields. That's exactly why mixed plastic is so tricky. If you fed only pure polyethylene into the reactor, you'd get a stable 80% oil yield by weight of feedstock. With mixed plastic, that number bounces between 50 and 65% depending on batch composition. And there's no way to predict more accurately without chemical analysis of every ton. And that kind of analysis costs money. Real money. The vapor coming out of the reactor is a mixture of hydrocarbons of different sizes. It passes through a fractionation column where it separates by boiling point, almost like at a regular oil refinery. The lightest fractions are gases. They don't condense and get burned immediately in a burner to produce heat that's fed back into the reactor. At this stage, the plant is practically energy self-sufficient. It heats itself with its own gases. The middle fractions remain as pyrolysis oil, a dark, slightly viscous liquid that smells roughly like you threw a plastic bottle on a campfire and let it burn completely. The heavy fractions settle out as fuel oil or a waxy substance. And there's still a solid residue left over, carbon black or technical carbon. It gets pressed into pellets and sold to manufacturers of rubber products or pigments. There's another technical hurdle worth explaining: chlorine. Chlorine actually hides in a ton of different packaging, in dyes, additives, adhesives. When plastic with chlorine gets into the reactor, the chlorine reacts with water and forms hydrogen chloride, an extremely aggressive acid. It eats through the steel reactor walls from the inside in about 6 to 12 months instead of the projected 10 to 15 years. Replacing a single reactor costs several $1,000s and weeks of downtime for the entire production line. So chemical analysis of incoming plastic and chlorine monitoring is literally a matter of plant survival. While I was walking through the facility, one detail struck me: sensors everywhere. On every pipe, every valve, every welded joint, there are sensors for temperature, pressure, and gas composition. This entire system feeds into a central control room where 3 operators watch screens displaying roughly 300 parameters simultaneously. If pressure in any reactor jumps above the calculated value by more than 5%, an automatic valve releases the excess. If temperature drops below 2.5 degrees, cracking quality decreases and the oil comes out heavier. That's bad. If the temperature exceeds 900 degrees, gasification kicks in. Oil yield drops to 0, and all you get is gas and carbon. The window between normal and something went wrong? Literally 50 degrees. In a reactor the size of a house. The pyrolysis oil produced here gets shipped in tankers to petroleum refineries, where it's blended with regular crude and goes through cracking, turning into naphthene and xylene, which are feedstocks for making new plastic. So theoretically, a shampoo bottle could circle back to polypropylene pellets and become a new bottle. Some major chemical companies, including several from the global top 10, are already buying this oil to manufacture plastic, and even paying a premium over conventional petrochemical feedstock, because they can print "made from recycled plastic" on the packaging, and for them, that's a marketing asset. The plant director told me straight up that even if they double their capacity and hit 400 tons a day, they'll be processing less than 0.1% of the world's plastic waste stream. The solution to the problem? Either drastically cut plastic production or build several thousand of these plants across the globe. Right now, neither is anywhere on the horizon. But this plant is proof that mixed plastic pyrolysis technology can actually work at industrial scale and turn a profit, even if it's razor-thin margins with really nerve-wracking logistics. I'm walking out of here with respect for the people doing this work, and a solid sense that 92%? That number's going to stay relevant for a long time. And you know what else is going to stay relevant? Subscribing to my channel! This metal tank, the size of a 10-story building, holds temperatures of -300 degrees. For it to carry rocket fuel or liquefied gas, there's no room for a single mistake in those walls. One microscopic air bubble in a welding seam, and the entire tank, weighing 150,000 pounds, becomes scrap. No fixing it after. No second chance. That's why every inch of that seam gets checked with X-rays, ultrasound, and helium. The gas with the smallest atoms in nature, finding microcracks where water wouldn't even seep through. And there's one moment in this process that makes the entire factory hold its breath. Today, I'm showing you inside. It all starts with choosing the metal, and this is the first stage where everything gets really expensive. Regular steel won't cut it here. It'll just die from the cold. We use special aluminum alloys, or nickel-rich stainless steel. These metal sheets are 3/4 of an inch thick, sometimes over 2 inches if the internal pressure is going to be seriously high. For example, manufacturing tanks for liquid hydrogen demand such metal purity that it's X-rayed before it even hits the welding table. Every sheet is marked and tracked, because if there's a void or impurity hiding somewhere in the structure, it'll become a rupture point under the cold. This is the foundation that holds all cryogenic equipment safety together. The welding process is a whole other story that makes a lot of engineers go gray prematurely. You can't just grab an electrode and weld 2 pieces of metal together. We use automated plasma or argon welding under a layer of special flux. The weld has to be stronger than the metal itself. Every inch of that weld goes through 3 stages of inspection. First, there's visual examination, then ultrasound, and finally, full X-ray scanning. We're looking for pores the size of dust particles. If even one air bubble is found in the weld, that entire massive tank gets sent to the scrap heap. There's zero allowance for fixing mistakes by welding over the top. That's the answer to how you ensure hermetic sealing and safety for decades ahead. Now we're getting to the coolest design feature. A cryogenic tank is actually 2 vessels, one inside the other. It's like a Russian nesting doll, where there's a gap 6 to 12 inches wide between the outer and inner shell. The inner tank holds the actual fuel, and the outer one protects it from the environment. But the real secret isn't the double walls, it's what's between them. There has to be absolute emptiness. We create a vacuum so deep that almost no air molecules remain. This prevents heat from transferring from the warm outer shell to the super cold inner one. Without this vacuum, liquid oxygen at -297 degrees Fahrenheit would boil faster than water in a kettle. To make this thermal barrier even more effective, we use what's called multi-layer insulation. Workers manually wrap the inner tank with dozens of layers of special foil and fiberglass. It looks like we're preparing a giant baked potato for giants. Each layer acts like a mirror, reflecting thermal radiation back into space. In other cases, we fill the gap between the walls with perlite, a volcanic sand we puff up into light white beads. It takes thousands of pounds to fill all the voids. Vacuum insulation testing takes weeks. Powerful pumps run day and night, sucking out air until sensors show the required level of vacuum. It's tedious, but a critical stage, because the vacuum is the only thing standing between calm gas storage and a massive explosion. The scale of these structures is mind-blowing. Some liquefied natural gas storage tanks stand over 100 feet tall and can hold millions of gallons of fuel. The weight of such an empty tank can reach 150,000 pounds. When it's filled, the load on the foundation becomes colossal. This isn't just a barrel on legs. It's a complex engineered structure with its own system of valves, sensors, and evaporators. All of this has to work in conditions where ambient temperature can swing from -30 to +110 degrees Fahrenheit, while inside, eternal winter reigns. The space industry is the main customer for these technologies. A rocket needs liquid oxygen and hydrogen to break free from gravity's grip. If a tank at the launch site springs a leak, a launch worth hundreds of millions of dollars gets scrubbed. But cryogenics aren't just for flights to Mars. Energy and industry consume these technologies in massive quantities. The whole world is now shifting to liquefied natural gas, and you can't transport or store it without these steel thermoses. Medicine, where liquid nitrogen is used to store biological materials at -320 degrees Fahrenheit, also depends completely on the quality of these welds. The most nerve-wracking moment at the factory? The helium leak test. Helium is a gas with incredibly tiny atoms that can slip through any microscopic crack where even water or air would get stuck. We pump helium into the inner tank at 500 pounds per square inch and scan the outer surface with special detectors. Sniffers. It's like finding a needle in a haystack, except if we find the needle, we have to explain to the customer why delivery just got pushed back a month. Nobody smiles here until the instrument shows absolutely zero leakage. This is the final exam for the entire factory crew. If you've ever wondered how cryogenic tanks work, here's the deal. They run on pressure differential. When we draw gas from the tank, a small portion of the liquid converts to vapor, maintaining constant pressure inside. It's a self-regulating system, but it demands perfectly calibrated hardware. All those valves and pipes are also made from special alloys and put through cold testing. We freeze them in liquid nitrogen baths to make sure they won't seize up at the worst possible moment. Another thing that blows your mind: how these giants get transported. When a tank 80 feet long rolls out of the factory gates, it becomes a full-on military operation. Special platforms with dozens of wheels slowly haul it to its destination. We have to be absolutely certain that during all that bumping on the road, the inner tank doesn't rip away from its supports. Those supports, by the way, aren't made of metal. They're made of special composite plastic, because metal conducts heat way too well. It's another tiny detail that shows just how complex the manufacturing really is. Right now there's a lot of talk about the hydrogen economy, and that means demand for these tanks is going to explode thousands of times over. But the number of facilities that can maintain these quality standards remains incredibly small. This isn't production you can scale up overnight. It takes years to train a welder to work with these alloys, and even longer to dial in the vacuum systems. This is a world where we're playing very dangerous games with physics, and so far, we're winning. I hope you found it fascinating to look at these steel giants and understand why they cost as much as a small fleet of luxury cars. This is where the ability to use our planet's most energy-efficient fuel is born. We walked through the workshops, witnessed plasma welds, and felt the chill of future vacuum. It's been a wild journey into a world where minus 300 degrees is just a normal working temperature. Thanks for joining me on this tour. Hit that like button if you were blown away by the idea of holding a vacuum inside a tank the size of a house. Subscribe to the channel, because we've got plenty more factories ahead where they create things most people don't even know exist. We'll show you a world made of steel, fire, and incredibly precise calculations. See you in the next review, where we'll be hunting for engineering truth once again in the roar of working machinery. Take care and keep your pressure in check. Every year, the world builds massive icebreakers and liners that weigh as much as entire neighborhoods. But did you know their heart no longer beats inside the hull? Engineers took an insane step. They ripped out a 30,000 horsepower engine, capable of powering a city of 25,000 people, and dropped it straight to the ocean floor in a steel capsule weighing as much as 2 Boeing 747s. This is an incredibly complex mechanism, where a rotor misalignment of a fraction of a millimeter can tear metal to shreds. Watch this video to the end, and you'll discover the shipbuilder's biggest secret. What fatal assembly mistake they hide underwater forever, and how an invisible enemy can destroy this beast in just a couple of days. From the outside, it looks like a massive metal tail bolted to the bottom of a ship. But inside, a full-fledged electric motor. They don't install it in the ship's hull, like they've done for decades. Here it's the opposite. The motor is immediately submerged in water, hermetically sealed in a steel casing, and made to work right there in the ocean. That's why this design is treated almost like an underwater vehicle. The idea to move the engine outside the ship's hull appeared relatively recently, although engineers themselves had been thinking about it for decades. Back in the mid-20th century, shipbuilders tried to get rid of long shafts, gearboxes, and complex mechanical transmissions that took up enormous space inside the vessel and lost part of the power. The real breakthrough came in the late 1980s, when Finnish engineers working on icebreakers for northern seas proposed a radical solution: relocate the electric motor directly into a rotating pod beneath the hull. The concept was developed by specialists at a shipbuilding company searching for a way to make vessels more maneuverable in ice. The first experiments looked risky. The motor needed to be completely isolated from seawater and made to run for years without maintenance. In 1890, the first working units appeared, and within just a few years, the technology started being installed on actual icebreakers. When it became clear that the rotating thruster allowed ships to move in practically any direction, cruise liner builders quickly adopted the system. Since then, this design has gradually changed the idea of where exactly a ship's heart should be located. Not inside it, but directly beneath it. From the outside, it looks like a massive metal tail bolted to the ship's hull. But inside is a full-fledged electric motor. It's not placed in the ship's body, the way it had been done for decades. Here it's the opposite. The motor is immediately lowered into the water, sealed hermetically in a steel casing, and made to operate right there in the ocean. That's why this structure is treated almost like a submarine vessel. I walk past sections of the hull that, just a few hours ago, were separate steel plates, each one several inches thick and weighing thousands of pounds. These are curved metal sheets several inches thick, already pre-rolled, so the future capsule will have a smooth, streamlined shape. Cranes slowly lift these elements and bring them together, like assembling an underwater projectile. Between the parts, they leave a narrow gap where the weld goes. During welding, sparks fly everywhere, and the metal glows orange. Workers move slowly, going over every foot of the joint several times. First, the inner seam is formed, then the outer one, after which the surface is ground down so no protrusions remain that would create water resistance. When the hull closes up, it already looks like a smooth steel torpedo. After that, inspection begins. The seams are examined with ultrasound and X-rays, searching for even the tiniest pores inside the metal. Any suspicious section gets cut out and welded fresh. Then the capsule is sealed and pressurized to levels way beyond what it'll face underwater. If there's a weak spot anywhere, it'll show up right away. Only after that is the hull cleared to handle years of work in cold seawater and constant ice impacts. Once the steel capsule is fully welded and pressure tested, they need to install the electric motor, the main power source for the future vessel. And that's when you realize just how massive everything is in marine engineering. Before installation, the motor sits on a special platform and looks more like part of a power plant than ship machinery. Its diameter is nearly 10 feet, and it weighs so much that regular lifting equipment isn't even considered. Only heavy overhead cranes do the job. The rotor, the rotating part of the engine, gets lifted separately. This massive metal ring with copper conductors weighs more than a fully loaded truck. The crane starts moving so slowly, it's almost invisible to the eye. The operator works off signals from several engineers standing on different sides of the housing, constantly monitoring the component's position. There's no room for sudden movements here. Even a fraction of an inch displacement could mean misalignment that'll show up during operation as severe vibrations. They literally lower it inch by inch, constantly measuring clearances with laser instruments. Bearings and support elements are already installed inside the housing, and all of them have to align within thousandths of an inch. If the engine shaft doesn't line up perfectly with the geometric center of the capsule, rotation will create an imbalance. After the rotor's been set, engineers won't let that crane move for a long time. A whole series of checks begins. They measure alignment, hand rotate the shaft several times, listen for the sound of metal contact. Sometimes they lift the engine again and adjust its position, spending hours on just a few millimeters of shift. Everyone here understands that once the casing closes, there's no getting back inside, so perfect precision matters more than speed. When the engine finally settles into place, the whole assembly suddenly looks complete. An empty steel shell transforms into a real powerhouse. This is the moment you could call the birth of a system that will soon spin a propeller, turn a multi-thousand-ton vessel, and run for years underwater, where no human will ever see it again. And so more people can see my channel, please subscribe and comment on the video. Modern installations can pump out up to 22 megawatts of energy. That's equivalent to over 30,000 horsepower. For perspective, one of these engines could power a small town of 25,000 people. A fully assembled installation, engine and propeller combined, can weigh over 320 tons, or more than 700,000 pounds. That's the weight of 2 Boeing 747s. The propeller attached to this pod often measures over 22 feet in diameter. Each blade on that propeller weighs as much as a full-grown elephant. Once the engine is securely tucked inside its steel casing, the moment of truth arrives, mounting the propeller. If the pod itself is the muscle, the propeller is the hand pushing against the water. And here we circle back to those head-spinning scales. Each blade is forged from a special alloy of bronze, aluminum, and nickel. This metal has to be strong enough not to bend under thousands of tons of water pressure, yet smooth enough not to create unnecessary turbulence. The blades arrive at the capsule on special pallets, each one wrapped in protective film like a piece of jewelry. Installation is done using hydraulic pushers. The propeller is mounted onto the motor shaft protruding from the capsule, and here precision is once again measured in thousandths of an inch. Any misalignment will cause the propeller to vibrate at high speed, and that vibration will simply destroy the engine bearings in a matter of days. When the propeller finally seats into place, it's secured with a massive nut tightened with a force that's hard to even imagine. After that, a streamlined cap is installed on the propeller hub. This ensures the water flow past the propeller stays perfectly smooth. The entire assembly is then coated with a special paint that prevents marine organisms and barnacles from attaching. Because even a few inches of buildup on the blades can reduce engine efficiency by 5 to 7%, which translates to losses of hundreds of thousands of dollars per year. You can find in ordinary dirt that contains so much energy, 2 pounds replaces 6 million pounds of coal. A rock you shouldn't touch with bare hands, controlled more strictly than gold, and determines whether entire cities have power in winter. This is uranium ore, the planet's most controversial geological resource, simultaneously saving us from climate catastrophe and threatening nuclear apocalypse. Let's dive into a world where geology collides with nuclear physics, and ordinary stone can change the fate of civilization. Let's start with what uranium ore actually looks like. If you're picturing something bright green, glowing in the dark like those mutant movies, I hate to break it to you. Most uranium ore looks like regular gray or yellowish-brown rock, sometimes with a greenish tint, sometimes with black spots, but nothing particularly mind-blowing. You could walk right past this stuff in the mountains and never even know it's radioactive. True, there are minerals like uraninite or torbanite that have a brighter yellow-green color, but that's more the exception. Real glow happens, but not from the uranium itself. Some uranium minerals fluoresce under ultraviolet light. They light up bright green or yellow. Geologists use this to find deposits. They shine UV lamps in the dark, and the ore gives itself away with that glow. Looks straight up cosmic, especially in caves, where the walls suddenly burst into neon colors. But the main feature of uranium ore isn't its appearance, it's what's inside. Uranium-238 and uranium-235 are isotopes that slowly decay, releasing radioactive radiation for billions of years now. 1 gram of uranium emits around 12,000 radioactive particles per second. Not enough to kill you instantly, but enough to build up a dangerous dose over years if you constantly carried a rock like that in your pocket. Uranium is found everywhere, in rocks, soil, water, even seawater. The average concentration in Earth's crust is about 3 parts per million. That means in every ton of ordinary dirt, there's roughly 3 grams of uranium. But for industrial mining, you need concentrations at least 100 times higher, from 0.3% and up. Deposits like that are rare and only form under specific geological conditions. The richest deposits are found in Kazakhstan, Canada, Australia, Niger, and Namibia. Kazakhstan leads in production, about 45% of global output. Canadian deposits in the Athabasca Basin, contain ore with uranium concentrations up to 20%. That's fantastically high. For comparison, most deposits have between 0.1 and 1%. How do you mine uranium ore? There are two main methods: traditional shaft mining and in situ leaching, which sounds like something from a sci-fi movie but actually works. In the first case, you dig a mine or an open pit, blast the rock with explosives, load it onto dump trucks, and haul it to a processing plant. Just like any other ore, except with radiation. Miners work under special conditions: constant radiation monitoring, dosimeters on every worker, limited time in high radiation zones. The air in the mines can contain radon, a radioactive gas released when uranium decays. It's constantly pumped out by powerful ventilation systems. Without this, miners would receive dangerous radiation doses in a matter of months. Now, about in situ leaching. Instead of digging a mine, they drill boreholes straight down to the ore deposit at depths of 300 or 600 feet. Through some boreholes, they pump in a solution, usually sulfuric acid with an oxidizer, or soda solution, depending on the type of ore. This solution dissolves the uranium right there underground. Through other boreholes, they pump out the solution that now contains dissolved uranium. At the surface, they extract the uranium from this solution using chemical methods. Underground leaching is cheaper, safer for miners, and less destructive to the environment. You don't have to haul millions of tons of rock to the surface. That's how most uranium is extracted in Kazakhstan. But the method only works for certain types of deposits where the ore sits in porous sandstone that a solution can filter through. After extraction, the ore needs processing. It's crushed, ground up, and also treated with acid or alkali to dissolve the uranium. What you get is a solution containing uranium, along with a bunch of other elements: iron, calcium, sulfur, rare earth elements. This solution is purified, and the uranium is precipitated as a concentrate called yellow cake. Though it's not always actually yellow, it can be greenish, brown, or black depending on the impurities. Yellow cake. That's uranium oxide with a concentration of about 80% uranium. Looks like a powder or a sintered mass. This is already a concentrated product that gets shipped to the next stage of processing. But it's still natural uranium, a mix of isotopes, where uranium-238 makes up 99.2% and uranium-235 only 0.7%. And for nuclear fuel in most reactors, you need to enrich uranium-235 up to 3 to 5%. Uranium enrichment, that's a separate high-tech industry, wrapped in secrecy and international controls. First, yellow cake gets converted into gas. It's the only uranium compound that easily transitions to a gaseous state under normal conditions. Though normal conditions here means a temperature around 140 degrees Fahrenheit with a slight increase in pressure. Then, this gas is run through thousands of cascades of centrifuges or gas diffusion plants. The centrifuges spin at around 100,000 revolutions per minute, so fast that the outer edge moves at nearly the speed of sound. At this rotation speed, heavier molecules containing uranium-238 concentrate slightly more near the walls, while lighter ones with uranium-235 stay closer to the center. The difference is tiny, which is why thousands of sequential stages are needed. The entire enrichment process takes months and consumes enormous amounts of electricity. A single enrichment facility can use as much power as a medium-sized city. That's why these plants are built next to major power stations or in countries with cheap electricity. And this is where geopolitics comes in. Those same centrifuges can be used to enrich uranium, not to 5% for power plants, but to 90% and beyond for nuclear weapons. That's why the international community tightly controls who gets access to these technologies. The Atomic Energy Agency conducts inspections, verifies that countries are following agreements and not building weapons under the guise of peaceful energy. Enriched uranium gets converted back into solid form, uranium dioxide. From it, they press small cylindrical pellets roughly half an inch in diameter and about 2/3 of an inch long. These tiny pellets contain as much energy as half a ton of coal, or around 130 gallons of oil. Hundreds of these pellets get loaded into long metal tubes made of zirconium alloy, fuel rods, and hundreds of rods form a fuel assembly for the reactor. A single modern nuclear reactor, 1 gigawatt of power, holds about 100 tons of uranium fuel. That's enough for 3 to 4 years of operation. During that time, the reactor generates enough electricity to power a city of 1 million people for those entire years, all from 100 tons of uranium. By comparison, a coal plant with the same output burns through roughly 10 million tons of coal over that same period. But there's a dark side. Spent nuclear fuel is the most dangerous waste humanity has ever created. After 3 to 4 years inside a reactor, the fuel becomes saturated with fission products, radioactive isotopes like cesium-137, strontium-90, iodine-131, and many others. Some of them stay radioactive for thousands of years. A single fuel assembly radiates so much that it can kill a person in minutes from just a few feet away. Spent fuel is first stored in water pools right at the plant. The water cools it and shields the radiation. After a few years, once the most active isotopes have decayed a bit, the fuel can be moved to dry storage, thick-walled containers made of concrete and steel. These containers need to last hundreds of thousands of years, until radioactivity drops to safe levels. Where and how to store them that long? A question humanity still doesn't have a good answer to. Some countries reprocess spent fuel, extracting unburned uranium and newly created plutonium, which can be used again. France, the UK, Japan have such facilities. But reprocessing is expensive, complex, and creates additional risks of nuclear material spreading. The US decided not to reprocess and to simply store spent fuel, waiting for a solution to the problem in the future. Control over the uranium fuel cycle, from mining to disposal, is a matter of national security. Countries with a complete cycle gain energy independence, but also the potential ability to build weapons. That's why the spread of these technologies is tightly controlled by international treaties. The Nuclear Non-Proliferation Treaty recognizes 5 nuclear weapon states and prohibits others from developing nuclear weapons, though it allows peaceful use of atomic energy. But reality is more complicated. India, Pakistan, North Korea built nuclear weapons without signing the treaty or by violating it. Iran is developing a uranium enrichment program, claiming it's for energy, but raising Western suspicions. Israel has nuclear weapons, though it doesn't officially acknowledge it. Uranium ore and the technologies to process it have become tools of global politics. Uranium mining also has environmental consequences. Tailings ponds, massive waste piles left after uranium extraction, contain radioactive elements, heavy metals, and chemical residues. If improperly contained, they contaminate groundwater for decades. There are stories of towns abandoned due to radiation pollution from uranium mining. For example, the city of Melusu in Kyrgyzstan is surrounded by millions of tons of radioactive waste from the Soviet era, which still poses a danger today. But there's another side to this. Nuclear power provides roughly 10% of the world's electricity with virtually zero carbon emissions. In France, nuclear plants generate 70% of the country's electricity, giving it one of the lowest per capita carbon footprints among developed nations. In the context of the climate crisis, nuclear energy is viewed as a necessary component of the transition to a low-carbon economy. How much uranium is left on Earth? Identified reserves stand at around 6 million tons, enough for 1 to 200 years at current consumption rates. But that's only what's already been found and is economically viable to extract. Potentially available resources are far greater, including uranium in seawater. There's roughly 4 billion tons of it there, though extraction is still very expensive. Ever wonder where trains go when they get too old for the tracks? This isn't like Grandpa's old car quietly rusting away behind the barn on the farm. A locomotive is a mountain of steel and copper weighing 450,000 pounds. Leave one of these bad boys sitting around, and it'll outlive your grandkids without even rusting properly. Today, we've come to a special facility where these steel giants take their final journey. This is a place where raw power meets surgical precision, and where everything that was once the pride of the railroad gets transformed into cold, hard cash and raw materials for new skyscrapers. We're going to watch how they dismantle monsters that spent decades hauling thousands of tons of freight across the entire country. It all starts with what we call environmental cleanup. A locomotive isn't just an iron box. It's basically a chemical warehouse on wheels, and none of that stuff is good for grass and trees. Before the guys with giant shears get to work, every fluid gets drained from the machine. Just picture these numbers. One large passenger or freight train can hold up to 5,000 gallons of diesel fuel. On top of that, there's another 400 gallons of engine oil and 300 gallons of coolant. That's a whole lake of chemicals that needs to be pumped out very carefully. Workers use special pumps that suck out every last drop, because even a single oil stain could trash the entire facility's reputation with environmental agencies. It's long, messy work, but without it, nobody's allowed to cut metal. But the really interesting stuff is hiding behind the walls. Inside a single locomotive, there's about 5 miles of copper wire. Copper is a recycler's treasure because its market price is astronomical compared to steel. Workers strip away the casing and pull out entire bundles of cables weighing thousands of pounds. It's tough manual labor because machines haven't yet learned to snake wires out of the tight channels of the fuselage quite so cleverly. And now, hold on tight, because we're moving to the heart of our iron beast. The locomotive engine, a 16-cylinder giant the size of a small minivan. One of these engines weighs about 35,000 pounds. To get it out, you have to remove the entire roof of the locomotive. A giant crane lowers its claws, hooks this block, and slowly lifts it into the air. It looks stunning, because you're watching something that produced 4,000 horsepower just hanging above the ground. If this engine can still be saved, it'll be sent for a major overhaul and serve another 20 years somewhere on a ship, or as a backup generator for a hospital. But more often than not, it goes to scrap too. They dismantle it into parts, aluminum pistons separate, steel block separate, cast iron components separate. Nothing here gets thrown away just like that. When the locomotive is just an empty steel box, my favorite tools enter the scene: hydraulic shears. Picture a massive excavator, but instead of a bucket, it's got something like T-Rex jaws. These shears clamp down with a force of several million pounds. They just roll up to the train frame and start biting into it like we bite into a chocolate bar. 2-inch thick steel gives way with such a crunch you can hear it half a mile from the yard. It's a really lively process. The excavator operator works the joystick so skillfully, it's like he's just playing a video game. He chomps off chunks of metal, weighing 2,000 pounds, and neatly stacks them in piles. This isn't just destruction, it's a very deliberate strategy, so every piece of metal fits into the furnace for melting down. Speaking of the frame, it's the strongest part of the entire train. It's made from solid steel beams designed to withstand massive loads during operation. Hydraulic shears sometimes can't handle it, and that's when workers with gas torches step in. The flame temperature there reaches 6,000 degrees Fahrenheit. Sparks fly 20 feet in every direction, and the metal just flows like water. It's incredibly hot work. Workers wear special silver suits that reflect heat, because standing next to that fiery point is like climbing inside a working grill. They cut the frame into 5-foot sections to make them easier to transport. And what about the wheels? Each wheel set is a massive piece of machinery where a single wheel weighs around 2,000 pounds. A locomotive typically has 6 of these pairs. They're removed either right at the start or at the very end, once the body's been dismantled. The wheels are made from incredibly tough hardened steel, so they don't cut them with shears. They haul them to a special press that simply crushes them or send them straight for remelting. It's extremely dense metal, and it's highly valued at steel mills. Don't forget the generator. A train is really a giant power plant on wheels. The engine spins a massive coil of copper wire that produces current for the electric motors on the wheels. This generator weighs around 8,000 pounds, and there's so much copper in it that you could buy yourself a pretty nice new car with what it's worth. They dismantle it very carefully because copper can't be mixed with steel. If even a little copper gets into new steel, it becomes brittle and completely useless. That's why sorting is rule number 1 at this facility. Now let's look at the cars. Passenger cars take way longer to dismantle because there's so much junk: upholstery, toilets, glass partitions, leftover food, and old magazines. Not as fun as cutting up a locomotive, but the numbers are still impressive. One empty car weighs around 120,000 pounds. Most of that weight is the frame and the wheel trucks. The car walls are usually pretty thin. Hydraulic shears tear through them like cardboard boxes in just minutes. In one workday, a yard like this can devour up to 10 cars, turning them into neat piles of sorted metal. When all this steel chaos wraps up, the yard is left with nothing but empty tracks and massive piles of scrap metal, sorted by type. Black steel in one pile, stainless steel in another, aluminum from high-speed train shells over there, and in a special locked container, precious copper. Then trucks roll in, or sometimes even other trains, to haul it all away to steel mills. There, these chunks get tossed into furnaces where temperatures hit 3,000 degrees Fahrenheit, and within a few hours, that old locomotive becomes molten steel. From that steel, they'll make rebar for buildings, parts for new cars, or even new rails. It's the incredible circle of life for metal. We're standing here, surrounded by sparks and thunder, watching something that once crossed continents become something new. This is a friendly place, as long as you respect the safety rules, because everything around you is trying to either burn you or crush you. The workers here are cheerful. They love their jobs and often joke that they're dentists for trains, just pulling out the railroad's bad teeth. But in reality, this is a highly complex logistical operation where every pound of metal has to be in the right place. Here's something wild. Breaking down a single locomotive from start to finish takes about 3 days if you're moving fast. When you factor in every stage, from draining the fuel to that final press of the remnants, it's incredibly well-coordinated work. One dismantling center like this can process up to 200 locomotives a year. That means hundreds of millions of pounds of metal get returned to the economy instead of just cluttering up the land. It's profitable, it makes sense, and honestly, it looks insanely cool. At the end of our tour, I want to say this: trains never truly die. They just change form. Maybe the lid on your lunch can today was once part of the braking system on a massive freight train thundering across the Arizona desert. In the world of engineering, nothing disappears without a trace, and that's genuinely amazing. You and I just watched hydraulic power defeat the strength of hardened steel and saw how humans control this enormous metal chaos. Every year, the world mines over 900,000 tons of rare earth metals. Without them, not a single smartphone, electric car, or wind turbine would work. But there's one place where most of them are born. Baiyun Obo, a massive quarry in the heart of China that supplies 70% of all the rare metals on the planet. Here, the earth glitters with metallic dust, and every dump truck hauls raw material for the future. But behind this shine hides a dark truth. Lakes of toxic waste, and the price nature pays for technological progress. Stick around till the end, and you'll discover how dust and poison create the foundation of modern civilization. The story of Baiyun Obo started back in the 1920s, when geologists discovered a strange ore in this area, a mix of iron and minerals unknown at the time. In the 1950s, Chinese scientists realized that hidden here was a treasure trove of rare metals: neodymium, praseodymium, cerium, yttrium, and lanthanum. Since then, Bayun Obo has become the heart of China's strategy that would eventually turn the country into the undisputed leader of the global rare earth market. Every year, about 270,000 tons of rare earth concentrate are mined here, more than all other countries combined. It all starts simply. Massive dump trucks the height of a 2-story building pull up to the edge of the quarry, where giant excavators with buckets like a dinosaur's mouth rip out chunks of monzonite ore. Each bucket can hold over 100 tons. The dust rises in columns, and it feels like the very air here is saturated with metal. But extracting the ore is just the beginning. The real value is hidden in microscopic inclusions of rare earth minerals. Their share in the rock is only a few percent, so after extraction, the ore is crushed and sent to processing plants, where a complex chemical story begins. First, the ore is ground to dust, then subjected to flotation, a process where particles suspended in water are separated using reagents. Rare earth particles stick to air bubbles, rise to the top, while the rest settles to the bottom. This is just the first step, because the concentrate still contains plenty of impurities: iron, calcium, fluorine. Next comes chemical extraction, which transforms the concentrate into high-purity oxides. This is an extremely complex process. In specialized reactors, the ore is treated with acids, usually sulfuric or hydrochloric, sometimes with the addition of fluoride compounds. After this, the resulting solution is separated into fractions using organic solvents. Each element, neodymium, praseodymium, cerium, has its own chemical quirks, so the process requires dozens of sequential cycles of extraction, precipitation, filtration, and drying. It's these oxides that then go into the production of permanent magnets, the main consumer of rare earth metals. For example, one iPhone might contain less than 1/10,000th of an ounce of neodymium in the speakers and vibration motor. In a modern wind turbine, nearly 1,400 pounds of this element. And here's the wow fact. Just 1 gram of neodymium can provide a magnet for a turbine that generates electricity for roughly 1,000 homes. It sounds like an energy miracle, but it has a flip side. The problem is that chemical processing of rare earth ores is extremely toxic. Every gram of pure metal means tons of waste. In the Bautu area, near Bayun Obo, real waste lakes have formed. Black, acidic bodies of water where radioactive elements, fluorides, and heavy metals accumulate. They're visible even from satellite. Even with modern cleaning technologies, chemical processes leave their mark on the environment. Local residents tell stories that, over the past decades, dust from the quarry and processing plants has changed the soil color, and grass around the area has been growing worse. However, the Chinese government is taking measures, implementing closed-loop water systems, controlling acidic runoff, and converting some facilities to new, green technologies, where instead of traditional acids, they use ionic solutions and membrane separation. All this is being done not just for environmental reasons, but also because China aims to maintain its dominance in the global rare earth metals market. Today, it accounts for 70% of global production and over 90% of finished oxide and magnet production. Other countries, the US, Australia, Vietnam, Malaysia, are trying to develop their own deposits, but they haven't come close to Chinese scales yet. Bayun Obo has become more than just a quarry. It's a symbol of the technological era, where Earth transforms into smartphones and ore becomes electric wind. Right here, among mountains of metallic dust, the elements that power digital civilization are born. There's a certain irony in this. In the quest to create a green future, humanity has become dependent on one of the dirtiest industries. Magnets for electric cars and turbines, batteries, solar panels. All of this requires metals extracted from places like Bayun Obo. And the greater the demand for clean energy grows, the deeper this giant wound in the earth becomes. Despite this, for China, Bayun Obo is a source of national pride. Thousands of people work here, and the territory itself is equipped with modern infrastructure, conveyor systems, automated drilling rigs, chemical plants that operate almost without human involvement. On the surface, sensors are installed that track air composition, and in reservoirs, pollution levels are monitored in real time. Every dump truck descending into the quarry is part of a giant machine that supplies the world with energy, data, and sound. And when we hold a lightweight smartphone in our hands, it's worth remembering that a piece of this device, maybe even that very magnet in the speaker, was once dust in the Mongolian desert. Neodymium is one of the most famous, and at the same time most mysterious rare earth metals. It's a silvery white, shiny, fairly soft metal that easily oxidizes in air, so it's usually stored under a layer of oil, or in an inert atmosphere. Sounds unremarkable, but this element has become the quiet engine of the modern technological revolution. Without neodymium, wind turbines, electric cars, headphones, laptops, and even rockets wouldn't work. In pure form, neodymium doesn't have the magnetic properties it's valued for. They appear when it's combined with iron and boron, forming an alloy. This is the material used to make the most powerful permanent magnets on Earth. One neodymium magnet can hold weight hundreds of times its own. In industry, it's called a supermagnet, and for good reason. It's what makes compact electric motors, miniature speakers, and highly efficient generators possible. One study indicates that between 2001 and 2021, Bayun Obo supplied about 60% of neodymium from China's total neodymium extraction. On one hand, Bayun Obo is a remote, harsh, and dusty place. On the other, it evokes an almost magnetic curiosity in those who want to see what modern civilization looks like in its raw material form. Bayun Obo today is not just a mine, but an entire complex with its own small town, a rare earth elements museum, and even a special viewing platform from which you can see the giant pit going hundreds of feet deep. The flow of tourists here is small by Chinese standards, but steady. These are mainly engineers, geology students, bloggers, eco-tourists, and those fascinated by industrial landscapes. In 2019, local authorities even declared Bayun Obo part of the Industrial Heritage of Inner Mongolia route to show how mining and processing have transformed the region. In tourist brochures, this place is called the heart of the rare earth planet. The road to the quarry leads through endless plains and low hills, where the wind almost never stops. The air carries the smell of metal, and from a distance, the quarry looks like a giant amphitheater, where Earth plays the starring role. Tourists aren't allowed close to the mining zone. It's too dangerous, but there are several safe spots from which you can take photos. The most striking moment is when quarry dump trucks slowly move at the bottom of the pit. They look like toys. The scale is so massive. Every year, billions of bolts get manufactured worldwide, so many that you could wrap them around the Earth thousands of times. But hidden in that ocean of metal, there are a select few that cost hundreds of dollars apiece, and literally have lives depending on them. Today, I'm taking you to a place where an ordinary bolt transforms into something far greater. A component that withstands extreme temperatures, crushing pressure, and even the vacuum of space. There's no factory noise here, but there is something else. Something they don't talk about openly. And if you stick around till the end, you'll understand why a $500 price tag is just the tip of the iceberg. The first thing that hits you right when you walk in? Silence. For some reason, I was expecting noise, like you'd get in a regular machine shop. But here, everything's calm. A few machines, 3 or 4 operators, and this feeling like you didn't just walk into a factory, you walked into a lab. Actually, that's exactly what it is. A lab. That also happens to be a factory. Let me walk you through how every bolt begins. The raw material is a specific nickel-chromium alloy that has to be ordered ahead of time and arrives in rods about 3/4 of an inch in diameter. One of those rods weighs around 20 pounds. It costs roughly $250, and that's before anyone's even touched it. The material isn't chosen randomly. It can withstand temperatures up to 2,000 degrees Fahrenheit, won't deform under pressure of 150,000 pounds per square inch. And here's the kicker. It doesn't lose toughness, meaning it won't go brittle like glass. A regular semi rumbles down the highway. Nothing special, no markings whatsoever. Thousands just like it roll through Connecticut every day. Inside, on wooden pallets bound with metal straps, lie the rods. Not dumped in a heap, not just thrown together, each layer separated by wooden spacers so the rods don't touch or scratch each other. Because a scratch on the raw material surface is already a detected defect that later gets damaged or cut away. One pallet, typically 40 to 60 rods, depending on length. A pallet like that weighs around 1,200 pounds. The truck can carry 6 to 8 of these pallets, meaning one trip hauls roughly $80,000 worth of material. Yet the truck itself looks no different from one hauling pens to a supermarket. At the factory, the truck backs into the loading dock, a small bay with a single door, sized specifically for one trailer. The driver backs up, the dock locks click into place, and then the forklift takes over. The operator grabs the pallet, hauls it to the raw material warehouse, a separate room with controlled temperature and humidity, because the alloy can't pick up moisture before processing. There, each pallet gets a paper tag with the batch number, delivery date, and material certificate, a document from the supplier listing the exact chemical composition of that specific melt. Without that certificate, the bars don't even make it into the plant. The driver can wait at the gate all day. And this is where things get interesting. The stuff you don't see from the outside. Before a bar hits the machine, they cut off a small chunk, about an inch long, and send it to the in-house lab for incoming inspection. They check hardness, examine the structure under a microscope, sometimes run a spectral analysis. Takes 2 to 4 hours. Only after the lab gives the green light does the batch get accepted and move into production. If the result doesn't match the certificate, they return everything, even if the difference is minimal. They cut a blank from the bar stock. A CNC machine removes material layer by layer. One blank is roughly 4 inches long. Cutting takes about 20 minutes per piece, and during that time, the machine makes approximately 2,000 individual movements with different tools. The chips that remain get collected. They're worth money too. Next, heat treatment. The blank goes into a furnace and holds at 1,750 degrees Fahrenheit for 4 hours. This is what's called annealing, a process that relieves internal stress in the metal that built up during cutting. Skip this step, and the bolt can have micro cracks invisible to the naked eye, but under load, they become a big problem. After the furnace, the blank gets cooled down, not in cold water, not in open air, but in specialized chambers with a controlled atmosphere where the temperature drops at a rate of 50 degrees per hour. The entire cooling cycle? That's another 8 hours. Now here's where it gets interesting. Thread cutting. The threads on these bolts aren't standard. They're engineered for a specific application, and in some cases are the customer's own proprietary design. The thread pitch might be, say, 28 threads per inch. That's an extremely fine pitch, ensuring maximum load distributed across the entire length of contact. Thread cutting is done on that same CNC machine, but now with a different tool, a carbide-coated threading tap. Cutting speed here is super low, around 30 revolutions per minute. Nothing gets rushed here. After the threads are cut, every bolt gets checked with a thread gauge. If the gauge goes in with the right amount of force, good. If it's too easy or too tight, the bolt goes back for rework or gets scrapped. If a bolt fails inspection, they don't try to fix it. They just start making a new one. Next up, final mechanical finishing. That's polishing the seating surfaces. Under the bolt head, there's a ring zone about 3/60ths of an inch wide that gets smoothed down to a surface roughness of 2 microinches. That's 50 times thinner than a human hair. For comparison, your average bolt from the hardware store has a roughness anywhere from 100 to 200 microinches, and nobody bats an eye. But here, This zone carries contact stress after the bolt gets tightened, and if it's uneven, microscopic movement can start, fretting as engineers call it, and over time the bolt will loosen. Can you imagine? Such massive work, but it's like jewelry. The coating is a whole separate deal. The entire bolt gets a nickel coating, 1 to 2 thousandths of an inch thick, through electrodeposition. Parts get dunked in a solution bath, and a direct current runs through it. Nickel gradually settles onto the surface in an even layer, about 20 millionths of an inch per year. The whole procedure takes 3 to 6 years, depending on the thickness required. After that, they check it, measuring thickness with an ultrasonic probe at 2 to 4 points across the bolt's surface. If there's more than a 10% deviation anywhere from spec, the bolt goes back for recoating. Now, where do these bolts actually go? Aviation is one of the main buyers, engine and landing gear fasteners. Then there are submersibles, where threaded connections have to handle pressure at depths of several thousand feet without corroding. There are clients from the nuclear industry, and there are a few projects in the space sector the factory doesn't really want to talk about. They just say, limited disclosure contract, and smile. When I asked how many bolts they make per day, the answer surprised me. 20 to 50 pieces. That's it. The factory doesn't chase productivity records, but each bolt passes through an operator's hands at least 7 times during the production cycle, which takes a total of 3 to 5 working days. Some bolts take a week to make, if the customer wants X-ray inspection and fatigue testing on top. That's a separate procedure. They load the bolt cyclically, 100,000 tension and compression cycles, watching for any cracks. I asked one of the operators if this all seemed like overkill for a bolt. He looked at me without much emotion and said, "This isn't a bolt. It's a system component whose failure costs more than our entire factory." Short and to the point. So there's your $500 a piece. And after that tour, I don't think it's expensive anymore. You're the best. Subscribe so you don't miss the next factory. It's gonna be even more interesting. Drop a comment saying where you're from, and maybe next time I'll swing by your state. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches, cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs, or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are 2 main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions. Underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive up front, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonker's lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centres, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. Every year, over 1,000 giant ships are sent worldwide for scrapping, each weighing up to 50,000 tons and stretching nearly 3 football fields in length. It's like dismantling an entire floating city, with hundreds of miles of cables, tons of toxic substances, and metal worth millions of dollars. One mistake, and an environmental disaster is inevitable. But here's the most amazing part. Inside each of these massive vessels hides something that turns scrapping into a real treasure hunt. Workers risk their lives among plasma cutters and toxic fumes to extract these valuables. What exactly are they looking for? And why have some countries turned ship graveyards into a multi-billion-dollar business whose dark side everyone keeps quiet about? Stay tuned. What you'll learn next will make you look at every ship in port with completely different eyes. Why is ship recycling so important? Vessels that we typically imagine as enormous floating megastructures can be nearly 1,000 feet long. Their weight sometimes reaches tens of thousands of tons, making them among the largest man-made objects created for sea travel and cargo transportation. But beyond their massive dimensions, these ships have extremely complex internal structures. Hundreds of feet of cables, pipelines, shafts, and various safety and comfort systems, plus countless different elements and mechanisms that perform different functions. This entire architecture isn't just scrap metal, but a complex organism that must be very carefully and properly dismantled when the ship reaches the end of its service life. It's critically important to properly remove all hazardous substances from the vessel that may have accumulated during its operation. These can be bioactive substances, toxic paints, fuel residues, lubricants, chemicals that, if handled improperly, can contaminate the sea, soil, and air, causing serious environmental problems. Without proper preparation, dismantling such a vessel can turn into a natural disaster. However, scrapping these maritime giants also has a very bright positive side. The metal from which the ship is made is excellent and valuable raw material that can be recycled and returned to production. This metal is used for building houses, machines, construction structures, and also for creating new vessels. This way, it's possible to reduce the need for smelting new steel, save energy and resources, and also reduce the amount of waste. Metal recycling from ships becomes an important link in the closed loop of modern industrial economy. Scrapping such huge objects also makes it possible to free up ports where old ships are standing, so new, modern vessels can take their place. This allows optimizing the work of naval bases and promotes fleet renewal. Additionally, proper recycling helps reduce operational costs for maintaining old ships and improves environmental standards in the maritime industry overall. The ship is delivered to special ship graveyards. These are usually coastlines with shallow water or special slipways. These locations aren't chosen randomly. Shallow water coastlines allow easy approach of the ship to shore, where it can be safely moored and dismantling can begin. Often these are small bays or beaches where the giant vessel is specially brought, so it doesn't interfere with maritime traffic and doesn't damage port infrastructure. Slipways, in turn, are large platforms or special structures where the ship is placed for dismantling on land. They're equipped with everything necessary for convenient and safe work: crane equipment, metal cutting tools, waste removal systems. One of the main tasks for specialists is ensuring environmental safety. After all, during operation, the ship accumulated many substances that, if handled carelessly, can harm the environment. These can be not only lubricants and fuel residues, but also toxic paints or chemicals. Therefore, the entire dismantling process begins with removing all such substances. Fuels and lubricants are drained into special containers and taken away for recycling or disposal to avoid getting into water or soil. Similarly with electronics and furniture, everything that could potentially harm nature is removed as a priority. This stage requires speed and maximum caution so that environmental standards aren't violated. After the ship is cleared of all hazardous and household items, the direct dismantling of the hull begins. And this is the most complex and dangerous part. Using special plasma cutters and gas torches, large steel structures begin to be cut into small pieces. This involves both hand equipment and heavy machinery, cranes, lifts, special manipulators. Plasma cutting allows very precise, fast and efficient metal division that will later go for remelting. The dismantling process itself happens sequentially, stage by stage, starting with the most hard-to-reach or dangerous zones. Metal sheets, beams, decks, and internal partitions are carefully separated so as not to damage structures that might still be needed for analysis or recycling. The complexity is that giant elements are often unevenly distributed and may be under tension, and due to corrosion or hull deformation, some parts can unexpectedly drop or fall at any moment. It's also important to emphasize worker safety. During plasma cutting, hot sparks and toxic fumes arise, requiring special protection from workers, respirators, special clothing, and constant air monitoring. A small mistake or neglect of rules can lead to serious injuries and accidents. Therefore, at every step, the process is regulated by strict safety rules, and the entire site is covered by fire suppression systems and medical support. Dismantling the hull and main steel structures of the ship is, without doubt, an extremely important and complex stage of scrapping a giant vessel. However, after this large body of work is completed, the job doesn't end. Ahead lies another massive phase that requires no less attention and certain skill, as it concerns dismantling and sorting countless smaller, but no less valuable and complex materials. One of the most massive and complex processes is working with cables. The ship contains hundreds of miles of cable networks that provide power and communication between all systems. These are powerful steel cables with insulation made of plastic, rubber, and possibly using non-ferrous metals. Cables don't just remain at the recycling site, they're carefully removed, processed, and sorted. Separating the metal core from insulation materials makes it possible to send pure copper or aluminum for remelting, and the insulation layer for recycling as raw material for new polymers. Workers must act very carefully not to damage long cable pieces, and also observe safety techniques due to the presence of residual substances or rust. Another important category of materials is insulation materials that line or fill the ship's walls, technical rooms, and pipelines. Insulation is often made from special materials: mineral wool, polyurethane foam, or basalt wool. These substances help control temperature inside systems and ensure safety when working with hot or cold components. After removing insulation, it's sorted and sent to specialized enterprises where these materials can be recycled or disposed of without harming nature. Working with ventilation systems also requires thoroughness. Ventilation pipes and units that were used for air conditioning and circulation in different parts of the ship are dismantled and cleaned of dust, lubricant residues, or other substances. Metal elements of systems typically undergo quality remelting, and plastics or rubber often become raw materials for new products. Special attention is paid to water supply systems and sanitary installations. On board the ship are complex shut-off mechanisms, pipelines, fittings, mixers, tanks, and other equipment. Pipe parts and equipment are carefully separated, cleaned of sediment, lubricants, and other contaminants to be sent for remelting or appropriate recycling. After all, these materials may contain toxic substances, so their disposal or recycling happens strictly according to regulations. No less important is dismantling equipment from the engine room. There are engines, generators, pump systems, turbines, and other complex machinery that typically has significant weight and contains large amounts of metals, including non-ferrous ones. Such equipment is mainly repaired and reused or dismantled into parts, some of which undergo recycling. In individual cases, engines even go for sale as used spare parts, avoiding becoming scrap metal. Furniture, household appliances, lighting, and other interior items of the ship also aren't just thrown away. They're removed and sorted. Wooden, metal, or plastic parts undergo separate recycling or disposal. In some cases, furniture, if it's in good condition, is sold for reuse, and all paints, varnishes, and certain polymer materials are taken for environmental recycling to reduce pollution. In every country, asphalt is just a road, but in Dubai, it's a challenge to nature. Here, air temperatures reach 122 degrees in the shade, while the road surface heats up to 160. Regular asphalt would melt within just a few days, but engineers found a way to make it survive. Polymers that hold their shape even at 176 degrees, geotextile membranes that breathe, and sensors that detect defects before human eyes can spot them. Why don't these roads melt like ice in the sun? And what strange technology did they test to make them actually dry after rain? Watch till the end. The finale will surprise you. Standard asphalt consists of stone aggregate and bitumen, a dark, thick substance that holds the mixture together, making it uniform and strong. However, bitumen has one weakness. It starts to soften at temperatures around 113 degrees Fahrenheit. For countries with moderate climates, this isn't a problem since road surfaces rarely reach such heating levels. But Dubai has completely different conditions. There, summer air can heat up to 122 degrees in the shade, while the road surface under direct sunlight can reach 160 degrees. Under such conditions, regular asphalt would literally behave like warm rubber. It would become soft, start deforming under vehicle weight, and in places simply slide off slopes. Plus, sharp temperature changes between scorching days and relatively cool nights would cause cracks to appear. In countries where occasional short heat waves occur, people might not immediately notice these processes. Sure, we sometimes get 104 degrees in summer, but such temperatures don't last long, and the surface deteriorates slowly, gradually. In Dubai, however, high temperature isn't just present, it's constant and stable for several months. This means asphalt is under continuous stress, and if you don't account for this factor, the road literally won't survive. That's exactly why engineers had to find a solution that would allow asphalt to maintain its shape even under extreme heating conditions. They replaced regular bitumen with modified bitumen, with polymer additives that change its physical properties. Such bitumen holds its shape at temperatures up to 176 degrees Fahrenheit. This means even when the road surface heats up to maximum levels, the material still remains stable, doesn't flow, and doesn't change structure. The difference might seem small at first glance. What's a few dozen extra degrees? But this exact difference makes Dubai's roads smooth, even, and durable, even when it's almost impossible to breathe from the heat around you. So what is this modified bitumen? The process is based on mixing bitumen with polymer additives. Polymers act like a reinforcing network at the molecular level. They stretch the bitumen structure, making it more elastic and heat-resistant. As a result, the asphalt doesn't soften. It maintains stability and shape even when heavy bus or truck wheels press on it for hours. The mixing process also isn't limited to just adding polymers. It's crucial to properly select the stone aggregate composition. Stones of different sizes create a framework-like structure, and bitumen here acts not as the main material, but rather as what connects the elements together. If the aggregate is selected incorrectly, bitumen will have to take on too much load, and even the modified mixture will lose stability. Therefore, asphalt composition is always a precise calculation of material ratios that don't just connect, but work as a unified system. But asphalt is just the surface. Hidden beneath it is a multi-layered sandwich that determines the road's durability. The first layer is sand, but regular sand won't work. It's mobile, can shift, and the road would lose its evenness within months. So sand is stabilized by mixing it with cement or special substances that make the mixture less mobile. Next comes a crushed stone layer that provides hardness and distributes load. Special geotextile fabrics can be laid between layers, preventing settling and material mixing. Geotextile works as a membrane that allows water to pass through, but doesn't let soil particles mix. This keeps the construction stable for many years. The way asphalt is actually laid also plays an important role. Work is usually done at night when temperatures are lower. This is necessary so bitumen cools evenly and gains the required hardness. If you lay asphalt during daytime heat, its surface will cool unevenly, creating stress in the structure that will eventually lead to microcracks. After laying, roads are regularly checked using special machines equipped with sensors and thermal imaging cameras. If sections are found where temperature is too high or irregularities appear, they're repaired immediately, not waiting until the problem becomes visible to drivers. Experiments with cooling coatings deserve special mention. In some districts, asphalt is painted or covered with a special compound that reflects sunlight and reduces surface heating by 10 to 15 degrees. This is important in pedestrian areas since road surface temperature affects how hot the air gets at foot level. This way, even a regular walk becomes less exhausting. In Dubai, roads aren't left unattended until large potholes appear. Control happens constantly and systematically. Special vehicles with measuring equipment travel highways and city streets, recording the smallest irregularities. Sensors read surface deviations, and computers compare them to standards. If there's suspicion of overheating or beginning deformation, the section is checked with thermal imaging cameras. High temperature indicates that bitumen is losing rigidity, and the surface might start settling. Thanks to such monitoring, repairs are done not when it's too late, but when the first changes begin. Repair work is conducted mainly at night when temperatures are lower and material cools evenly. This extends the road's service life and avoids repeated damage. The approach is based on the idea that infrastructure should work continuously, not wait for the moment when it becomes a problem for drivers. According to Dubai municipality data, after switching to polymer-modified mixtures, the number of deformation waves on roads decreased by approximately 40% during the first 2 years. Meanwhile, road surface service life increased on average from 7 to 10 years to 12 to 15 years before the first major repair. This significantly reduces overall infrastructure costs. Although initial polymer asphalt installation costs are higher by approximately 15 to 20%, long-term savings can reach 50% due to reduced repair needs. There's also data on experimental light reflective coatings being tested in residential areas and near pedestrian zones. On average, such coatings reduce road surface temperature by 10, or even all 14 degrees, depending on conditions. According to observations, in areas with cooling roads, air temperature at pedestrian foot level also drops by 2 to 3 degrees, reducing thermal load on people and making outdoor stays more comfortable. Statistics also show that, with early detection of surface microdefects, their elimination takes on average 3 to 6 hours, while if you wait for visible damage to appear, repairs can last from several days to several weeks and require closing road sections. Therefore, the city focuses on regular monitoring. In 1 month, control vehicles can cover over 80% of the city's road network. Dubai once tested asphalt that absorbs solar energy, then radiates stored heat at night to dry roads faster after rare rainfall. Turns out, the surface works like a giant thermos. During the day, it accumulates energy, and at night gradually releases it. The experiment showed such roads can dry 30% faster. And this is really needed, because after desert rain, water doesn't absorb into the ground, but can stand on asphalt for hours or even days. So the technology solves a problem that doesn't even exist in most countries. You know how this experiment ended? Every year, the world melts down more than 16 million tons of silicon metal, a material without which modern civilization would simply grind to a halt. It makes steel stronger, aluminum lighter, and solar panels possible. But here's something almost nobody knows. To create just 1 ton of this metal, furnaces operate at temperatures exceeding 5,400 degrees Fahrenheit and consume as much electricity as hundreds of American households use in a month. So why does this silent giant hide a diamond structure inside? And what discovery about silicon will change your understanding of technology if you stick around till the end? Industries use metallurgical-grade silicon as a foundational material for creating ferroalloys, particularly ferrosilicon, which gets added to steel to improve its strength, corrosion resistance, and ability to withstand high temperatures. How steel deforms, its elasticity, and behavior under load largely depend on how silicon dissolved in the metal matrix behaves. Metallurgical silicon is also critical for producing aluminum alloys, where it's responsible for reducing weight and improving the alloy's ability to maintain its shape when heated. For example, in cast aluminum parts for automobiles, the silicon content can reach anywhere from 12 to 14% by weight. Another key application is obtaining purer silicon suitable for electronics and photovoltaics. Metallurgical-grade silicon serves as the starting point for producing polysilicon, which gets purified to impurity levels in the parts per billion range. This ultra-pure material is what they use to form ingots and wafers for microchips and solar panels. Demand in this sector has shot up dramatically in the US over recent decades, driven by renewable energy expansion and the needs of data centers. To put the scale in perspective, manufacturing a single solar panel module that's about 11 square feet requires roughly 6 or 7 pounds of silicon in the form of high-purity polycrystalline material. Metallurgical-grade silicon has additional applications too. It's used in chemical manufacturing to synthesize silicones, which are needed for sealants, lubricants, medical devices, household products, and electrical insulation components. It serves as the starting material for silanes, compounds that act as coupling agents between organic and inorganic materials, ensuring stronger surface bonding in composites. Certain types of silanes are used as part of adhesives and coatings that help extend the service life of structures in humid or corrosive environments. Technological progress constantly raises the bar for metallurgical-grade silicon, since purity, grain size, and consistency of properties directly impact the quality of the final product. In American industry, research continues on optimizing electric arc furnaces to cut energy consumption, as well as on utilizing carbon monoxide byproducts. On top of that, companies are developing ways to recycle silicon production waste to bring part of the material back into the cycle and reduce emissions tied to mining fresh quartz. All of this makes metallurgical-grade silicon one of the foundational industrial materials. Without it, Modern electronics, transportation, and energy sectors couldn't keep up their current pace of development. To turn mineral oxide into metal, you need extremely high temperatures and a carefully controlled reduction reaction. This is done in large electric arc furnaces that operate at massive temperatures and consume enormous amounts of electricity. The furnace is loaded with crushed quartz along with carbon-based reducing agents. Most commonly, these are charcoal, coke, or various carbon briquettes, selected to ensure stable combustion and the right reactivity. Powerful graphite electrodes create an arc that heats the center of the furnace to approximately 5,430 degrees Fahrenheit. Under these conditions, ordinary rocks transform into active participants in the reaction. Silicon dioxide reacts with carbon, and as a result, oxygen is removed from the oxide. Gaseous carbon monoxide forms, while pure silicon transitions into a liquid state. The molten material is heavier than the surrounding charge, so it slowly settles to the bottom of the furnace, accumulating as a metallic mass. Once enough silicon is collected, it's released into special crucibles or troughs. As it cools down, the liquid metal solidifies into solid ingots, which are then crushed into smaller pieces that are easier to transport and process further. At this stage, it's crucial to maintain conditions that prevent impurities from oxidizing again or mixing with the cooled silicon. The raw material obtained at this point already has commercial purity of around 99%. This level of purity works fine for ferroalloys, but it's not enough for more demanding applications. Next comes the stage of refining the metal to higher purity. Silicon can be remelted in a vacuum or under an inert atmosphere, using various methods like sorption, zone melting, or chemical purification. The main goal here is to get rid of impurities like iron, aluminum, calcium, and sometimes phosphorus and boron. The impurity content is controlled with precision down to parts per million, because even a tiny amount of foreign elements can seriously affect the electrical properties of the final product. After purification, you get metallic silicon with the characteristics needed to produce alloys, silicones, or even purer polysilicon. The production process itself is energy intensive, so it's critical that the method ensures minimal heat loss and makes the most efficient use of electrical power. Modern furnaces come equipped with heat recovery systems and electrode feed control. This helps cut down overall energy consumption and boost productivity. Process optimization is a big deal here, because on average, making 1 ton of metallic silicon requires about as much electricity as several hundred American households use in a month. The quality of quartz sand plays a crucial role too. The purer the initial silicon dioxide, the fewer purification stages are needed after melting. Quartz with high impurity content can lead to increased energy consumption and greater furnace wear. That's why deposits supplying raw materials for the silicon industry must meet strict standards for chemical purity and mechanical uniformity of the material. Silicon, though it doesn't have gold's shine, is a true geochemical giant, an absolutely irreplaceable element. In terms of abundance in Earth's crust, it holds an honorable second place, losing only to a non-metal, oxygen. This means that, essentially, we live on a massive silicon-oxygen planet. It's hard to wrap your head around this, but this substance makes up a colossal 27.6% of our planetary crust's mass. Just imagine, almost every 4th ton of material we see beneath our feet is silicon or its compounds. It forms the backbone of entire mountain ranges and serves as the building material for countless minerals called silicates. This element isn't just filler, it's the foundation of our entire modern civilization.